Hi everyone, welcome back. So we have been studying about PN junction. In the last lecture we studied about PN junction under equilibrium. So there was no external bias applied. This was our PN junction under equilibrium, right? So there has been a built-in electric field that has been set up. Now this built-in electric field will make sure that amount of diffusion and amount of drift both are equals to each other and they are cancelling out each other, so total current would be zero. So this was our PN junction under equilibrium and we were having a particular depletion width. Okay, and that depletion width that depended on the doping level as well. So this was your P side, so this width was minus XP and this width was XN, right? Now what we are going to do, we are going to apply some external bias. That means some external voltage we are going to apply across this PN junction, so that will disturb its equilibrium. So the external voltage that we are going to apply, that will disturb its equilibrium. Now if I am connecting P side with positive and N side with negative, so if I connect the battery in this manner, that P side is connected with positive and N side is connected with negative, then it is known as forward bias. And if I am connecting P side with negative and N side with positive, then it is known as reverse bias. Okay, P positive, N negative, that means it is forward bias. Now what will happen in forward bias, what will happen in reverse bias, that we are going to check. In this video we are going to understand only the forward bias. So this was your semiconductor under equilibrium. Since you have applied this battery, now this battery would do something with the semiconductor and something would happen in this PN junction. Okay, what will happen, that we need to see. So we are going to understand about forward bias now. So this is our setup, this was our equilibrium condition. Now if I have applied the forward bias, let's see what happens. So before applying this forward bias, what was the scenario? There has been a built-in electric field in this direction. And that electric field is this much. Okay. What really happened? Holes were diffusing towards the N side and electrons were diffusing towards the P side. Both recombined each other, they made a built-in electric field and there was a depletion width available. So this was the condition under equilibrium. Now what I have done? I have applied a voltage. Now this voltage has to be distributed over this PN junction. What I mean to say is that what will be this voltage drop? From here to here. Let's just say this voltage I am saying that is 0 volt. So this voltage has to be VA volt. Is that clear to you? Let's just say VA was equals to 5 volt and I am saying that this is 0, then this VA would be 5 volt only. The 5 volt is exposed to the PN semiconductor or PN junction, you can say. Now you will notice a very interesting thing, that this particular side is having a lot of charge carriers. If more charge carriers are there, that means conductivity more. What does that mean? That means resistivity lower, or you can say resistance is lower. That means this particular region and this particular region is having lesser resistance. But you know that in the depletion region is depleted of charge carriers. That means this particular part would have less resistance, but depletion region would have very high resistance, and again this particular part will also have less resistance. So this particular resistance is known as sheet resistance. Okay, we call it sheet resistance, and somewhere you will see it is known as series resistance as well. So series resistance you can call it, or sheet resistance you can call it. And now this VA has been applied, this 5 volt has been applied across this particular junction. Is that understandable to you? I am just seeing one thing, that how that potential will be distributed. 5 volt will be distributed across PN junction, but where the most of the potential would go, this is what I am checking. So 5 volt has been applied here, and I know that, what do I know? That this R depletion is much larger. R depletion is much larger than RS. So what will happen? Whatever the potential that you are going to apply, most of the potential will be dropped here only. So if I call this as V forward, VF, then I can say that VF would be nearly equals to VA. Say yes or no? So most of the potential that you are going to apply, most of the potential will be dropped across the depletion width only, or you can say it will be dropped across the depletion region. Is that understandable to you or not? Okay, so let's remove this 5 volt. So is this point clear? That most of the potential has been developed here only. So whatever the external field that you are applying, most of the electric field would be find out in this particular region only. Most of the electric field will be find out in this particular region only. And what will be the direction? What will be the direction? Sir, here positive, this positive part is coming, and sir, here negative part is coming. So direction would be from positive to negative. This would be the direction of external electric field. So this is your E external. This is your E external. Now what you can see, the built-in and external both are opposing each other. Right? The built-in electric field and external electric field both are opposing each other. What does that mean? That means the effective electric field will become narrower. The effective electric field, the E effective, if I write down, that would reduce, right? That would be E built-in minus E external. Say yes or no? Right? And you know that Vf is nearly equals to Va. So can you write down V junction? What I am writing down? V junction. That means at the junction, how much is the total potential? So previously it was V built-in, but now it is V built-in minus Va. When there was no Va applied, then junction potential was, at the junction, the potential you are having were V built-in. Now it is V built-in minus Va, because some external voltage that you have applied, that is opposing the built-in potential. Built-in potential was set up in this manner, but now applied potential is in this manner. So now your effective junction potential has decreased. What does that mean? Do you remember the formula of depletion width? That was under root 2 epsilon by q. Everything remains same, doping and everything, epsilon remains same, everything remains same, but the junction potential has decreased. This junction potential, this has decreased now. Previously it was V built-in, but now it has become V built-in minus Va. And since here I will not write down Va, I will write down Vf. Okay, Va would be wrong. Va is the applied voltage, no? Vf is the voltage that is actually reaching towards the depletion region. So here I should write down Vf. Right? What is Vf? Vf is the actual potential that has been applied to the junction. Right? Va is the complete potential that you are applying. Now Vf is the potential that is reaching in the depletion region. So that is the Vf I will write down here. So here I will write down Vf, not Va. Okay. So what does that mean? The depletion width will be reducing now. So previously this was my depletion width. Previously this was the scenario of my depletion width. This was my XP node and this was my XN node. Now what will happen? This will shrink. This will shrink. So here I will keep this line. I will carry this line here. This line will come down here and this line will come down here. Depletion width has shrinked. Okay. Now sir, from where this extra hole would come up? Someone may have the query that sir, you are saying that depletion width is shrinked, like this depletion width is going down. I should not say going down. The depletion width has reduced. Depletion width has reduced. That means sir, this donor atom who has lost its hole, he is again getting back its hole. From where he is getting back his hole? So he is getting back his hole from the battery. Okay. From the now we will see that from the battery the current is flowing in this manner. So if current is flowing in this manner, that means current will be flowing in this manner. In the battery, current will be flowing in this manner. So if current is flowing in this manner, that means electrons are traveling opposite. So from here electrons will be supplied and from here holes will be supplied. Are you able to understand this point? So those holes and electrons are coming from the battery. Okay. So they will get back their electron and holes and the depletion width has reduced now. Now what will happen? What was the job of this depletion width? What was the job of this built-in electric field? This built-in electric field, this was the condition under equilibrium, right? This was your QVBI. This was the condition under equilibrium. So this built-in electric field was making sure that the amount of diffusion and the amount of drift both are equal to each other, right? This is what it was making sure, that amount of diffusion and amount of drift is equal to each other and they are cancelling out each other, so total current is zero. But now the depletion width has reduced. That means this barrier will be reduced now. Do you agree to this point? So let's make the energy band diagram under non-equilibrium, or I can say energy band diagram under forward bias. Now this barrier will be reduced. Why it will be reduced? You can see in other manner as well. Here there will be positive and here there will be negative. So negative multiply with negative, that means this energy has increased. Here the energy has increased, and positive multiply with positive. So whole energy is also increased. What I am saying, this positive has been applied here, this negative has been applied here. So negative multiply with negative, what will be the energy of electron? Negative multiply with negative, E equals to QE. So Q is also negative, V is also negative. Negative multiply with negative, that means this will be positive. So electron energy has increased. So when the energy of electron increases, what really happens? When the energy of electron increases, then this was the condition under equilibrium. When the electron energy has increased, that means this part would go up now. And when the whole energy increases, here what is the scenario? Sir, positive multiply with positive, positive multiply with positive, that means whole energy also increases. And I told you energy of holes increases in the downward direction. So this part would go down. So this was your equilibrium condition. Now what is the scenario? This part is going up and this part is going down. What really happen? This part goes up and this part comes down. That means the barrier between these two EC, that has reduced. The barrier between these two guys, that has reduced. So previously the barrier was QVBI, but now the barrier has become QVBI minus VF. And VF would be nearly equals to VA, right? So let's remove this arrow. This arrow is of no use. Just to make you understand, I made this arrow. VF would be nearly equals to VA. So can I simply write down VA only here? Okay. Well, let's put VF. So is that understandable to you? Okay, the barrier has reduced now. Since the barrier has reduced, now let me know which process would become dominant. Like reducing this barrier is helping whom? It is helping drift or it is helping diffusion. If you have studied the first chapter or first topic where we studied about introduction to semiconductor junction, then you will be able to tell like who is getting the help now, drift or diffusion. Diffusion is getting the help now, right? This is here a lot of electrons are there and here lesser electrons are there. So now these electrons will be able to move more freely. They will be able to diffuse here very easily. And what about these holes? Here there are more holes. Here there are more holes and here there are lesser holes. Now these holes will be able to diffuse here as well. That means this electric field, first this electric field was stopping these holes to go from here to here, and this was stopping these electrons to go from here to here, because previously this built-in electric field was very strong. If it was very strong, then what was happening? Electron said that, sir, I want to go here because of the concentration gradient. I want to go here because here there is more concentration, here there is lesser concentration, so I will always move from more concentration to less concentration. But what this built-in electric field said? Go back. Right? But now the effect of this built-in electric field has been reduced. So now some electrons will say that, sir, now I will diffuse. And similarly, some holes will say that, sir, now we will diffuse. So some holes from the P side will get into the N side, and some electrons from N side will get into the P side. Is that understandable to you? So let me make a rough diagram here. What is the scenario? Here there was junction, right? Here there was junction and depletion width has reduced. Depletion width has reduced. So what really happens? Here there were a lot of holes. Previously they were not able to diffuse. Now what these holes will say? That since the depletion width has reduced, or the total electric field that has been reduced, or better, yeah, EBI minus E external I can write down. Since this is reduced, now what I will do is that some of the holes will get here and they can diffuse, right? So holes will start diffusing from P side to N side. Similarly, there were a lot of electrons here, So electrons from the N side will start diffusing towards the P side as well. So similar thing electrons would also do. And now holes are diffusing towards this side and electrons are diffusing towards this side. That means because of both of them, there would be a diffusion current on this side. So yes or no? So the amount of current has increased now. Is that understandable to you? The current has increased. Okay. Why it was increased? Because of the applied external battery. What really happened? The internal electric field, what was the built-in electric field was there, that has been reduced. Since that built-in electric field has been reduced, what really happened? Previously the holes were not able to diffuse, electrons were not able to diffuse, but now since it has reduced, now electron will say that sir we will be able to diffuse. Now holes will say that sir we will be able to diffuse. So what really happened? It's like a lot of holes from the P side has been injected towards the N side. Can you say this statement? Let me repeat the statement again. What is really happening? It feels like that a lot of holes from the P side has been injected towards the N side, and a lot of electrons from the N side has been injected towards the P side. So electron injection and hole injection is happening from P side to N side and from N side to P side. Okay. So let's relate it to some other scenario that we have already seen. So in basic semiconductor physics, what we were seeing, like this is our N-type semiconductor. So what we did, we throw a light here. In this N-type semiconductor, there was certain number of donor atom. Okay, this was equals to the number of electrons, and then there were number of electrons in N-type semiconductor under equilibrium, and then there were certain number of holes as well. Right, that was equals to Ni square by Nd. So number of holes in N-type semiconductor under equilibrium. When we throw this light, what really happened? A lot of new holes came into action. A lot of new holes came into action here, right? Some electron also came. Electron hole pair was generated. So electron also came into action, hole also came into action. But what really happened with these holes? The excess was generated here, but these holes reduced with the distance. Do you remember this? Like here the excess holes were generated. At this particular point, your holes were Pn naught plus delta P0. But this particular thing reduced with the distance. Do you remember this? Do you remember writing down the expression of delta Px? That delta P0, but it will reduce with the distance. This is how we used to write down. Excess minority carriers. This was your excess minority carriers. So excess minority carriers were maximum at x equals to 0. But as you walk through the distance, they were reducing exponentially. So similar thing will happen here. A lot of holes will say that, sir, this depletion width has reduced, this electric field has been reduced. So sir, now I will be able to diffuse. So a lot of holes will get into N side. From here, a lot of holes are saying that, sir, now we will be able to diffuse. So from here, a lot of holes from P side will get into N side. So they will reach here. They will reach at Xn. They will reach at, holes have reached at x equals to Xn. But as they move along the N-type semiconductor, their density would decrease. Are you able to understand this point? We will draw the concentration plot. So this is how the concentration plot would come up. I am roughly drawing it as of now. So let's just say this is my Xn. This is my x equals to Xn. Okay, this was my x equals to 0 and this was my x equals to minus xp. This was your P side and this is your N side. So a lot of holes from the P side has come to N side. So they have come here. So here the electron concentration has increased. Sorry, here the holes concentration has increased because a lot of holes from the P side have come to the N side. But as you walk along the length, their concentration will decrease. It's same as the electrical injection. Your N-type semiconductor was there. What we did, we throw some light. Because of the light, electron hole pair was generated, but those electron hole pair, they diffused with the length. I should not say they diffused with the length, they recombined with the length. Basically, this is your N-type semiconductor. No. Every device wants to remain in the equilibrium. So N-type semiconductor, what he will say? N-type semiconductor will say that, sir, under equilibrium, I was having number of electrons equals to Nd and number of holes equals to Ni square by Nd. Sir, you are throwing some light here. Because of the light, electron hole pair will be generated. I am fine with that. But as the intensity of light goes below, Like as the intensity of light goes down, then I will make sure that this excess carrier that has been generated at x equals to 0, they don't see the effect later on in my length. So with respect to the length, these excess carrier concentration was reducing. So similar thing is happening here. What I am doing, basically I am pumping the holes from p side to n side. I am pumping the holes from p side to n side. So what this n side will say, that sir, you can pump the holes, here, but as you walk along the length, of a n-type semiconductor, you would see that their concentration is reducing exponentially. I will not let them stay. Here also the same thing happened. Here if I want a uniform concentration of excess carrier, then what I need to do? I need to throw the light from everywhere. From here as well, from here as well, from here as well. I told you, if you are doing the uniform illumination, then only the concentration of excess carrier would remain uniform, otherwise it will decay exponentially. So similar thing would happen here as well. A lot of holes from the p side would get into the n side, but at x equals to xn only you would see a lot of holes, but they will decay with the length. Is that clear to you? And since holes are moving, same thing would happen with electrons as well. A lot of electrons from n side would go to the p side. What p side would say? That sir, you are pumping electrons. I am fine with that. What you are doing, sir, you are pumping electrons from n side to p side, but p side will say that, sir, at x equals to minus xp, you can have excess electrons. But as you walk along my length, as you move along my length, their concentration will decrease exponentially because I will maintain my equilibrium. Is that understandable to you? Okay. Now let's discuss some misconceptions. First misconception is that people think whatever the applied voltage that we are having here, this applied voltage, this applied external field. So what people think is that this external electric field, which we have applied here, this external electric field is pulling these holes. Like basically, this is my PN semiconductor. Okay, I have applied some extra electric field here. I have given positive voltage here, negative voltage here. That means I have applied this E external here. Now this E external is pulling these holes, because where holes will move? In this direction. So this is a misconception. No, this is not that is happening. Why so? Because most of the applied external electric field is not going here. Most of the applied external electric field is going into the depletion region only. So the job of this external electric field is just to reduce the effect of this depletion region. This external electric field is not pulling these holes. Are you able to understand this point? This external electric field is not putting any amount of force on these holes. Even if it is putting, then very less amount of force it is putting on these holes. Because you know that most of the electric field has been put in the depletion region only. So there is this very high misconception from a lot of students that, sir, external electric field is applied like this. That means this field is putting some force on these holes. So that means this electric field is pulling these holes. Or similar thing can happen with electrons as well. So this electric field has been applied here. That means this electric field is pulling these electrons this side. No. Most of the part of electric field is going into this depletion region only. And since it is going into this depletion region, the job of this external electric field is just to reduce the effect of this built-in electric field. And because the effect of this built-in electric field has reduced, now the holes will be able to diffuse very easily. Is that understandable to you or not? So this external electric field was not doing the job that you were thinking. Because on the top level, what it may feel like that, sir, external electric field is applied. That means this external electric field is pulling these electrons. It is pulling these holes. It is pulling these electrons, and because of that, current is flowing. No, the current is flowing because of the diffusion. And why diffusion is happening? The current will flow because of the drift as well. There is drift component as well. There is diffusion component as well. We will discuss that. But as of now, what you can see, the depletion width has reduced, and now holes will be able to diffuse more freely. So this is the first misconception that a lot of students would have. Now second misconception that not only students have, a lot of educators also have. And that misconception is, let's just say my built-in potential was 0.7 volt. Okay, let's just say my built-in potential was 0.7 volt. Now I am applying this VA. Okay, let's just say I applied this VA equals to 1.1 volt. Okay, now you would be thinking that, sir, most of the VA is dropped across depletion region only. That means 1.1 in this direction has been applied, right? And previously I was having 0.7 in this direction. That means, sir, this 1.1 will overcome this 0.7. So now effective electric field I will have in this direction. Basically, someone would say that, sir, this external electric field will cancel out the effect of a built-in electric field. So eventually the electric field will become in this direction. Are you able to understand what is the doubt? That, sir, if I apply very high external bias, let's just say I have applied 1.1 volt and my built-in potential was 0.7 volt, and now I know that, sir, most of the part of 1.1 volt will drop down here only, and since most of the part has been dropped down across the depletion region, then what will happen? 1.1 will cancel out 0.7. That means effective 0.4 volt I will be having in the direction from P to N. Wrong. Okay. Never ever you will get, never ever this depletion width become 0. Like this VA will never be able to reduce the effect of built-in electric field. Why is that so? Because what did I say? Let's take it, let's understand the whole scenario with respect to an example. The example is that my built-in electric field is 0.7. Okay. So first I applied my external potential to be 0.1 volt. When I applied my external potential to be 0.1 volt, what really happened? Most of the potential went into the depletion region. Most of the potential went into the depletion region. So 0.7 minus 0.1, 0.6 was the effective, 0.6, here was the positive and here was negative. So 0.6 became the effective voltage. Since the electric field has been reduced now, E built-in minus E external, since the electric field has been reduced now, more holes will be able to diffuse, so current is increasing. Now if I increase this voltage, let's just say if I make it 0.3 volt, then what will happen? Then more field will be reduced, right? 0.3 will be exposed here. Now 0.7 minus 0.3, it would become 0.4. That means this built-in, the effect of built-in electric field has been reduced more. Basically this barrier will become even lower, and since this barrier is become even lower, then what will happen? More diffusion will take place and more current would rise up. So what do you understand? That as I am increasing VA, my current is rising up. Now let's just say I took VA at 0.7 volt only. Now what you will be thinking, that, sir, complete 0.7 will be exposed to V built-in, right? This complete 0.7 volt will be going here. But what do you think? What will happen? If you are increasing the VA potential, then current is rising up, no? And that current is flowing through these resistance as well. Although these resistance are low, but current is rising up, no? And we will see current will rise up exponentially. What I am saying, you said that, sir, most of the potential is applied across this depletion region. I am agreeing to this. VA is nearly equals to VF. Now, if this VA is very high, what does that mean? That means this PN junction is driving very high current. And since it is driving very high current, although this resistance is low, the current is high. So this will also take sufficient amount of drop. No, same goes for this one as well. This will also take sufficient amount of drop. And you know that VA has to be equals to 2I into RS plus I into R depletion. So these RS will always make sure one thing. What they will make sure? They will always make sure one thing, that the drop across R depletion, the drop in this built-in, the drop in this depletion width would never become more than the built-in potential. Okay, a very, very excellent point. Like a lot of people, what they would think is that, sir, if I keep on increasing this forward bias, then what will happen? This drop, this barrier would become 0, and if I increase it more, then the graph would become opposite. Like what people think, here EC would come and here this EC would come. The graph would become opposite, and in a lot of lecture I have seen this diagram as well. They make the graph opposite, like you can understand, no? V built-in minus VF. So it will keep on reducing, the gap reducing, and at some point the graph will become opposite. Absolutely wrong. It will never happen, because as you are increasing the forward bias, the current is also increasing, and the current will increase exponentially. And you can think as well, why exponential? Like, because if you are increasing the voltage, then what will happen? this built-in electric field, the effect of built-in electric field will keep on going down, going down. That means more and more holes will be injected here. More and more holes will be injected here. That means more and more current will flow. Because if more and more holes are coming here, what does that mean? More and more concentration gradient would be there. More and more concentration gradient would be there. That means more and more current would be there. So if you are increasing VA, then current is increasing. Now this increased current will be flowing through these RS as well. And these RS would always make sure one thing, that the drop across R depletion would always remain lesser than V built in. So always your VF would be less than V built in for sure. No matter whatever the amount of VA you are applying. Okay. VF will always be less than V built in. If someone says PN junction is my favorite topic, this is the first question I will ask him in some interview. What will be that question? That if I keep on increasing this VA, then what will happen inside the depletion region? So he might think that, sir, depletion width completely will be vanished. But depletion width will never be vanished. It might be very, very low, but minute depletion width will always be there. Okay? Some minute depletion width will always be there. And this RS would make sure that I will take a sufficient amount of drop across me, so that in the depletion width, that VF drop always remains lesser than V built in. Okay, so all this theory I have written. So first let's erase whatever that is not useful for us. So theory and everything has been written here. You don't need to worry about the theory, but let's make the notes a bit more clear. Okay. And yeah, one more thing you guys can let me know what this will be equivalent to. QVF, right? Basically, at the equilibrium, they were equal, right? Now, what made them apart? At the equilibrium, they were equal. Now, how they became apart? Because I applied VA. So, it should be equal to QVA. Right? Understandable? Very easy thing, no? They were equal. First, they were equal. I applied QVA, that's why they became apart, no? So, this has to be equal to QVA. Right? Or QVF you can write down, but I know that VA would be nearly equal to VF. Right? My bigger matter of concern would be VF. But in your gate examination, always you need to take VA would be equal to VF only. What I am saying, my bigger matter of concern would be VF, not VA. Why VF is the matter of concern? Because VF is the actual potential that has been dropped across a depletion region. VA is the applied potential. I don't care about the applied potential. I care about the actual potential that has been developed or that has been dropped across the depletion region. Because this potential only is reducing the effect of electric field. So my major matter of concern is VF, but in your gate examination, VF would be always equal to VA only. Okay? They will make sure that they will give the value in this manner that VF is equal to VA. So here better I should have written QVF, but let's put it QVA only, because I'm going to derive some expressions later on. And those expressions I will write down in terms of VA, not VF. Okay? So let's keep it QVA only. You can put QVF as well, but I hope you are able to understand the difference between VA and VF. What is the difference between VA and VF? The difference is that VF is the actual applied potential across the depletion region, and VA is the actual applied potential that user is applying. Okay, so all this theory and everything has been written here. So let's read out this theory. When a PN junction is forward biased, P side is connected to the positive terminal of the battery and N side is connected to the negative terminal of the battery. The applied voltage opposes the built-in electric field of the depletion region, therefore reduces the potential barrier across the junction. Right? As a result, the depletion region becomes narrower and the internal electric field becomes weaker due to the reduction in the barrier height. Holes from the P side will diffuse towards the N side and electrons from the N side will diffuse towards the P side. Okay, everything we already know, everything is understandable. When these carriers cross the junction, they recombine with opposite type of carriers on the other side, leading to a large flow of current through the diode. Did you understand? What is diode? Diode is PN junction only. Don't get confused with this word diode. Okay, so what is written here? When these carriers cross the junction, they recombine with opposite carriers on the other side and leading to a large current through the diode. What does that mean? That this was my PN junction. From here, a lot of holes came into action. These holes came here. Now you know that, sir, their intensity, not intensity, their concentration would decrease exponentially. Basically, if I draw their concentration plot, that we are going to draw only in some time, after 10 minutes only, we will draw the concentration plot. So you know that, sir, here most of the holes would be there, but as you go along the length, the concentration of holes has decreased. So why the concentration of holes has decreased? Because these holes have recombined with the electrons. Are you able to understand this point? Here there were more holes, and you see that, sir, after you move for the length of 5 LP, 5 diffusion length, like if you move for some length only, after some length you would realize that, sir, the hole concentration has nearly become equal to the equilibrium hole concentration. That means whatever the external hole that came into action, whatever the holes that were injected, they have actually recombined. And because of that recombination, the current has been flowing through the diode. Okay. It is important to note that most of the applied forward voltage drops across the depletion region, because this region is highly resistive due to the absence of charge carriers, while the neutral region have very low resistivity and they take a very small voltage drop. Thus, under forward bias, the diode offers very low resistance and the current increases exponentially with the applied voltage. So when you keep on increasing the applied voltage, what really happens? The depletion width becomes narrower and the built-in electric field, the effect of built-in electric field will keep on reducing. More and more holes will diffuse, and more holes will diffuse. That means they will go from p side to n side, and more electrons will go from n side to p side. Whatever the scenario that I am explaining with respect to the holes, the same scenario is happening with respect to the electrons as well. So don't get confused, okay? I will explain the scenario with respect to holes, but the same scenario is happening with the electrons as well. So from p to n, from n to p. So holes will be recombining with the electrons will be recombining with the holes, and because of that the current would flow. Okay. Right. So if y increased, why it will increase exponentially, that we will see with respect to mathematics. Okay. Sir, why exponential increase is there? Why this word exponentially? So with respect to mathematics, we will prove it. Don't worry about that. But you get to know one thing, that if I am increasing VA, the current would increase. Okay. Well and good. So let's remove this one. Now all the misconception that we are having. So first misconception I have written here. There is a common misconception that the applied electric field in the forward bias directly pulls holes from the p side towards the n side, or electrons from the n side towards the p side. In reality, the electric field does not drag the carriers across the junction. Okay. The job of this electric field is to reduce the built-in potential that would oppose the carrier motion. So this built-in potential was opposing the carrier motion. This built-in potential under equilibrium, this was saying that now electrons cannot diffuse, and whatever the amount of electrons are diffusing here, the same amount of electrons are drifting as well. So this barrier was the problem why the electrons were not able to diffuse or holes were not able to diffuse. But now this barrier has reduced. So the job of the external electric field was to reduce the barrier, not to pull the electrons. Okay. So once the barrier is lowered, the majority carriers that were already trying to diffuse across the junction can now do so more easily. Hence, the current in the forward bias is dominated by diffusion, not by drift due to applied field. The applied voltage simply makes diffusion easier by lowering the energy barrier created by the built-in potential. Right? So built-in potential was creating this much of barrier, but the applied external field has reduced the barrier. And because of the reduced barrier, what you can see, more electrons are able to diffuse, more holes are able to diffuse. Okay, why holes are diffusing in the downward direction? Because whatever the electrons do the process, they do the process in the opposite manner. For them, this is the motivation, and for them, going upward is the motivation. Right? Now, another common misconception is that depletion region will completely disappear if the forward bias voltage is increased continuously. But in practice, this will never happen. Because as the current increases with the forward bias, there is also a voltage drop across the neutral region due to their finite resistance. These resistance are known as sheet resistance or series resistance. Okay, and because of this, the voltage actually appearing across the junction is always less than the built-in potential. Okay, what does that mean? That your VBI would always be greater than VF. This will always be maintained. Therefore, the built-in field is never fully cancelled and the depletion region never becomes zero. Even at high forward bias, a small depletion region and a small internal electric field will always remain to maintain the charge balance within the junction. Okay, so always there will be a small built-in electric field, always there will be present no matter how high potential you apply. Is that understandable? So two common misconceptions are there for forward bias that we have cleared. So in your notes, in your older notes, if you have made some diagram like E external is less than E built-in or E built-in equals to E external or E built-in less than E external, if these kind of diagrams are there, then cut those diagrams, okay? Because I have seen in a lot of notes, this thing is happening in a lot of notes that E external would become greater than E built-in. So what will happen? Whatever that happens, that actually doesn't happen. Okay, always E built-in will be stronger than E external, always. Just it's that the external electric field is trying to reduce the effect of a built-in electric field, and the barrier is reduced. Now electrons will be able to diffuse more freely and holes will be able to diffuse more freely. If both are diffusing more freely, then we are getting some current, and more forward bias voltage would be there, more and more current we would get. Okay, I hope you are able to appreciate all these things. Okay, and all these things I have understood from NPTEL only. There is a 17-year-old NPTEL lecture. There all these things are mentioned. Okay, from IIT Madras. So that professor is having this much of knowledge 17 years back. Can you imagine? Professor S. Kalmarkar. Okay, Professor S. You write down IIT Madras, you will get the playlist. So he was having this kind of knowledge 17 years back. Can you imagine what kind of knowledge he would be having now? Like there are a lot of EDC playlists like from Naresh Imani sir, from Professor Digvijay sir, from ISC there is a playlist, from IIT Hyderabad there is a playlist, and those are very good playlists. Like every playlist is very good. But can you think of appreciating this guy? 17-year-old playlist is there. Like he made that those videos 17 years back, and there he is explaining these kind of concepts. In textbook you will not find out all these concepts, right? Okay, so can you imagine what kind of knowledge he would be having currently? Like at that time, no internet, nothing. Internet was not that much. Like internet was there, but it was not accessible to all the people, not all the time, right? Even textbooks were limited. Every resource was limited. And at that time, he was having this kind of knowledge for the subjects like EDC. So now he would, if he teaches, then I don't think anyone would even come nearer, right? So he is still teaching actually. He is still there in IIT Madras. You can read about him. You can go to, not as of now, complete this lecture. After that, you can do all these things. Yeah. So let's make the carrier concentration plot now. Okay. So this was our equilibrium condition. What I am considering? I am considering P+N junction. What does that mean? That means I am considering that Na is greater than Nd, because for Na equals to Nd we have already made the plot. So that's why I thought of making Na greater than Nd. Okay. So this was under equilibrium. Under equilibrium, what was the condition that was maintained? N into P equals to Ni square. Right. Let's just say Na was 10 to the power 16. That means this was your number of holes. So what will be your number of electrons? Ni I am taking as 10 to the power 10. So number of electrons will be 10 to the power 4. So this was your number of electrons in P side under equilibrium. That was equals to Ni square by Na. Right? Ni square by Na. Right? So this was 10 to the power 4. This was 10 to the power 16. Rough number I am taking. Like I want you to understand that why this graph is lowered, like why this graph is lowered, why this graph is upward. Now what will be your Nd? Na is greater than Nd, so let's just say Nd was 10 to the power 15. So if Nd was 10 to the power 15, that means number of electrons on the N side was 10 to the power 15. So what will be the number of holes? That would be 10 to the power 20 divided by 10 to the power 15. That means that would be 10 to the power 5. So this would be 10 to the power 5. Ni square by Nd. That is equals to number of holes on N side at equilibrium. So this was 10 to the power 5 and this is 10 to the power 4. So that's why I have made this as a bit upper side and this as a bit lower side. And 10 to the power 16 and this was your 10 to the power 15. Are you able to understand this point? Okay. If this is lesser, this would be more. If this is more, then this would be lesser. But always n into p equals to ni square, that will be maintained. So this diagram is clear to you, right? So I can make this diagram in a much clearer manner now. So this is your Na, this is your Nd, this is your Np node, this is your Pn node. And always one condition would be maintained, that is number of electron would be equals to, n into p equals to ni square. And it will be maintained in that depletion width as well. Okay, in the depletion region as well, not depletion width. In the depletion region as well, it will be maintained. This condition would be maintained, right? This time it will not meet at the junction, right? This time it will meet somewhere here. The concentration of electron and holes will decrease or increase exponentially. So where they will meet? Here they will meet, not at the junction this time. Okay, and along with that you can see that this depletion width I have made lesser and this I have made more. That means Xn naught is more than Xp naught. Why is that so? Because of this thing. Because doping on p side is more, that means depletion width on p side would be lesser, right? Now under forward bias, what is happening? Let's make the diagram under forward bias. So first thing is that depletion width would reduce. So depletion width has reduced, but still I need to make sure one thing: depletion width has reduced, but still your minus Xp, this Xp would be lesser than Xn, right? Xn would still be greater. So yes or no? This width has reduced, but still Xn would be greater than Xp. This will always be maintained, no? Both will reduce by the same amount. Both will be reducing by the same amount. Okay, so Xn would still be greater than Xp, right? There will not be much change in the majority carrier concentration. Like the number of holes here will remain the same. Number of holes here will remain Na only. Now someone would be saying that, sir, holes will be diffusing. No. Sir, you are saying that holes will be diffusing from p side to n side. So if they are diffusing, that means here the concentration should go down. No, battery will apply. Battery will supply the holes, right? From the battery, holes will be supplied. From the battery, electrons will be supplied. Electrons will be diffusing from n side to p side. So electrons will be going from n side to p side, but here there will never be any problem when it comes to the number of electrons. The number of electrons would remain the same. Who will apply? Battery will apply, right? Battery will supply the electrons. So battery will supply these electrons. So they will remain the same. This is the number of holes. Number of holes in p side, not under equilibrium, under forward bias. And this is your number of electrons on n side, not under equilibrium, under forward biased. Okay. Now what about the hole concentration here? At the equilibrium, what is the equilibrium condition? So at the equilibrium, I will expect the number of the number of holes to be Pn naught only. This is what I would be expecting at the equilibrium. But what will happen? From here, a lot of holes would come into action. So here I will get the increased concentration. I will get increased concentration, but eventually this increased concentration would decrease exponentially. Okay, so let's make the diagram a bit better now. Is that clear? Right? So at the equilibrium, the concentration was supposed to be Pn naught, but actually how much concentration you are getting? This much concentration we are getting. Now how much will be this concentration? That would be a good matter of concern. Okay, that's a very good question, that sir, how much will be this concentration based on the applied voltage? Sir, you are applying some voltage. Because you are applying some voltage, that's why this concentration is changing, no sir? So what will be this concentration? That means what will be your number of holes in n side at x equals to xn? This will be a matter of concern. Number of holes in n side at x equals to xn. Is that understandable to you? Okay. And here as well, some electrons will be diffusing from n side to p side. but this I will make a bit lower because this concentration is lower, no? So from some of the electrons from here to here, they are diffusing. And at the equilibrium, what I expected? At the equilibrium, I expected them to be NP naught. This is the plot we are making with respect to X. This is the plot we are making with respect to X. Okay. And another important thing is that this was made on log scale, but this is not the log scale, right? Exponential decay I am showing, that means it is not the log scale. On log scale, this decay would be linear. So this is on the log scale, but this is the linear scale. Okay. This we are drawing on linear scale, right? So at the equilibrium, number of electrons in p side, that should be equals to Ni square by Na only. So at the equilibrium, this is what I will be expecting. Here also I will be expecting Ni square by Nd. As you move along the length of a n-type semiconductor, this is your n-type, this side is n-type, and this side is p-type. So as you move along the length of n-type semiconductor, you would expect that equilibrium is maintained. But at the junction, a lot of holes from the p side have come to n side, and a lot of electrons from the n side have gone to the p side. So at the junction, there is some problem. But as you move along the length, their concentration would decrease. As you move along the length, their concentration would decrease. So always this will also be a good matter of concern. The number of electrons on p side at x equals to minus xp. So what will be this number? So now our target would be that we find out this number of holes on n side at x equals to xn. Is it the excess hole? What I am saying? PN xn. This is your number of holes on p side at x equals to xn under forward bias. So is it excess holes? No, these are not the excess holes. These are the total holes, right? Basically, your PN xn would be equals to the excess holes at xn plus equilibrium holes, right? This much is the excess holes, no? We will make the diagram again on the next page. It will be clear to you. Like what I am going to find out now. I am going to find out the total number of holes in n side at x equals to xn under forward bias. Is that clear to you? Okay. What I am going to find out? I am going to find out the total number of holes on n side at x equals to xn under forward bias. So what will be the excess holes? That I can find out very easily, because I know that under equilibrium this much holes were already there. PN naught holes were already there. What excess came into action? This much excess came into action. So this is the excess. Okay. So we will see that. We will make the diagram again on the next page. So let's not do anything here. We can just put this particular thing. Yeah. So people will be able to remember what is PN xn. That's it. Rest all things are fine. Now what we are going to do? We are going to see some mathematics. But along with that, we are going to make the diagram as well. What is this? This is your energy band diagram for forward bias. Sir, we joined EC with EC, EV with EV, but we did nothing with EFN. Sir, why we did not join like this? Sir, in my older course, I have joined it like this. Okay. If you have joined it like this in your older course, then have some patience. Let's understand it more beautifully. Okay. So this is our depletion region. No? This point would be, let's remove this. This point would be x equals to minus xp, and this point would be x equals to xn. Okay. Now let's talk about at x equals to xn. I am reaching at x equals to xn. Now what you would see at x equals to xn, if I make my PN junction as well, I am making my PN junction as well. Under forward bias, I am making it under forward bias. So you know that forward bias is also applied already. This is positive, this is negative, this is my x equals to 0, this is my p side, this is my n side. Under forward bias, I am making it. Now I know that at x equals to xn, the whole concentration has increased. although this concentration is not crossing the electron concentration. I am not saying that, sir, this concentration, this whole concentration has crossed the electron concentration. No, but the whole concentration has increased. No, right? Basically, at this point, whatever the whole concentration we are having, and at this point, whatever the whole concentration we are having. So here we are having more whole concentration. Here we are getting equilibrium condition only. So apart, like very far away distance from Xn, you are having equilibrium condition only. So this is fine. The gap between EC EFN is fine. The gap between EC and EFN at very far away from Xn, that is fine, because at very far away from Xn, you would know that whatever the excess holes that were generating here, they will have no impact at very far away from Xn. Right? They will have no impact at very far away from Xn. But at the Xn, at the junction, I should not say junction, at the edge of depletion, at X equals to Xn, you are having excess holes, right? If you are having excess holes, then the gap between EC and EFN should be increased or decreased? It should be increased, right? Do you remember one diagram like we discussed about Quasi-Fermi level? Quasi-Fermi level. So when this Quasi-Fermi level came into action? In the optical injection, right? There were delta P and delta N were coming into action. Because of this delta P, the concentration of holes got increased. Since the concentration of holes got increased, then we make two Fermi levels, EC, EV. One Fermi level was nearing EC and one Fermi level was nearing this was your EFN, this was your EFP in one semiconductor only, because of this excess holes. So similar thing is happening here as well. These excess holes are coming into action. That means now the gap between EC and EFN should increase. So at X equals to Xn, the gap between EC and EFN should be a bit more larger. Say yes or no? So here I will make my Fermi level, and as I move along the length, I would realize one thing, that is I am eventually going towards my quasi-neutral region only. This is my quasi-neutral region. That means I am going towards equilibrium condition only. As I move along the length, I am able to achieve the equilibrium condition, but here equilibrium condition is not maintained. Here the holes concentration is a bit more. That means my Fermi level would be a bit nearer to EV. Although the gap between EC and this point would be still lesser than the gap between this and this point. What I mean to say, at this particular point, the electron concentration is still more than the hole concentration. There is no doubt about that. Again, let me repeat the statement. At this particular point, the electron concentration is still more than the hole concentration. Once again, at X equals to Xn, the hole concentration is still lesser than the electron concentration. That's for sure. But if I compare this particular point and if I compare this particular point, let's just say this particular point is Xn plus some 2 micrometer distance. At this particular point, you would see that the number of holes are very much less. That means this graph is applicable. But here this graph will not be applicable, no? So here I need to make the graph in this manner. Is that understandable to you? Okay. And then you can carry the whole graph like this. Similarly, let's talk about at X equals to minus XP. Now, at your BTech level, even in the examination as well, they can join like this. But still I am like, I wanted to give more concept of Quasi-Fermi level, but still like in some textbook as well, in some notes as well, you would find out this kind of graph, but you would never see the explanation. But this is the explanation, that X equals to Xn, all the problem is happening at X equals to Xn. As you move along the length, the problem is being eradicated because equilibrium will be maintained, and anyway you cannot have excess holes. Whatever the excess holes that are coming from the P side towards the N side, those will be diffused. I should not say diffused, those will be recombined with the length as you move along the N-type semiconductor. So as you move along the N-type semiconductor, those electrons will be, those excess holes will be recombined with the electrons. Now someone would be thinking, sir, electron and holes are being recombined, so from where electrons are coming? Battery will be supplying. Here I am saying that whatever the excess holes are coming with the distance, they will be recombined with the electrons. So, sir, electrons will be using? No, we will not be losing electrons. Electrons will be coming from the battery. So, whatever the electrons that you are losing, battery will make sure that they apply these electrons. Okay, they supply these electrons. And whatever the holes that you are losing here, battery will make sure that holes will be supplied. So, supply of electron and holes will never be lesser. It's just that at the depletion, at the edge of depletion, there could be excess electrons, there could be excess holes. But as you move along the length, those excess electron and excess holes will be gone. Okay, so this diagram we are getting. If you are not able to understand it, still it is fine. No one will ask you this particular thing. But again, if you discuss at x equals to minus xp, at x equals to minus xp, what is the scenario at x equals to minus xp? Sir, the number of electrons has increased here. Although these number of electrons are never crossing the number of holes, we will always consider low level injection. That means these holes will never cross the majority carrier concentration. Those excess minority carrier concentration will never cross the majority carrier concentration. But still the number is pretty high. Here the number is pretty low. That means this graph is, this particular energy band diagram that you have made here, that is still fine. But at the edge of junction, you know that the number of electrons are pretty good enough. That means the gap between EC and EFN, or you should say the gap between EC and the Fermi level, the gap between EC and the Fermi level cannot be same as this gap. This gap has to be lesser, because here there are more number of electrons. So if this gap has to be lesser, what does that mean? That means, and as you move along the length, this gap will keep on reducing, and after a certain length, you would see that equilibrium has been maintained. So this is the scenario we are getting. So this kind of graph we will get. Okay, so in your notes, if it was made like this, then also it is fine. Okay, but at your BTech level, this much knowledge is fine. Like if you are able to make this diagram, then it is pretty good, and you should be able to explain as well that what is happening. That sir, at the junction, at the edge of depletion, minority excess carrier are coming from P side towards the N side. That means the hole concentration has increased. If hole concentration has increased, that means the gap between EC and the Fermi level should be increased. Whatever the gap that I am having here, this gap cannot be same. That means this gap has to be increased. And in the depletion region, this gap is maintained, and this gap is equals to QVA. And the whole problem is coming because of this guy only, because of this QVA only. So previously under equilibrium, we were maintaining this particular thing. The number of electrons and number of holes will always be equals to Ni square. Let's see, are we able to maintain this particular thing here or not? So that's why I do not make that what is happening inside the depletion region. Now we are going to see what will happen inside the depletion region. Okay. So I don't think I need this. Let's start with the mathematics. So I know one thing, that my EFI, here if I talk about, like here I will be having some EFI, no, intrinsic Fermi level, and here you would have your intrinsic Fermi level. So the gap between EFI and EFP, what that would be equals to KT ln number of holes divided by Ni, right? And the gap between EFN and EFI would be equals to KT ln number of electrons divided by Ni, right? If I join both of the equations, sorry, if I add both of the equations, what do I get? EFN minus EFP is equal to KT ln P into N divided by Ni square, right? For semiconductor under equilibrium, this was 0 because EFN and EFP were at the same level. But now in the depletion region, like here, if someone asks you what is the gap between EFN and EFP, you can say, sir, at this point, at this particular point, if I'm asking here, that what is the gap between EFN and EFP, you would say, sir, this much gap is there. But if I ask you in the depletion region, what I am asking, in the depletion region, how much gap is there between EFN and EFP? So what I am saying, in the depletion region, what is the gap between EFN and EFP? So that gap is QVA, right? So this is equation 1, this is equation 2. So now I am writing down for depletion region, what you are getting. So this gap is QVA equals to KT ln number of electrons multiplied with number of holes divided by Ni square. So what you are getting now, this KT can go here and you can see that, so number of electrons multiplied with number of holes is actually coming out to be Ni square e to the power Va by KT. There you go. When Va was 0, that means there was no external bias. At that time, what was the number of electrons multiplied with number of holes? That was Ni square. But now what you have done? Because of the electrical injection, this was known as optical injection. No? This we used to call it optical injection. Now this we call electrical injection because the holes from the P side are going into the N side because of the applied electric field. So this is known as electrical injection. So because of the electrical injection, inside the depletion region, the electron and hole concentration has increased, and that has increased in this manner. Now what is my matter of concern? My matter of concern is the boundary. My matter of concern is edge of depletion region, right? I want to find out the electron concentration and hole concentration at the edge of depletion region. So what I need to find out, at the edge of depletion region. That means first I will check at x equals to xn. So at x equals to xn, number of electrons at x equals to xn, number of holes, x equals to xn means it is n side, no? X equals to xn means it is your n side, right? So number of electrons in n side at x equals to xn multiply with number of holes in n side at x equals to xn would be equals to Ni square e to the power Va by, like if this is voltage, KT is not voltage, so Va by Vt I should write down, right? Because KT represents the energy, Vt is a better way, okay? Because it would be QVA by KT, no? QVA by KT. So KT by Q would be Vt only, so I can write down Vt here, right? Now in the n side at x equals to xn, what is the number of electrons you are getting? At x equals to xn, number of electrons in n side is equals to Nd. Do you agree to this point? At x equals to xn, number of electrons in n side is equals to Nd. Number of holes, this is something that I need to find out. Ni square e to the power Va by Vt. So PN xn. This derivation you are not going to find out even in the textbook, okay? I am telling, this derivation will not be there in the textbook. You would see in any notes you can check, or in any lecture you can check, like either they will not derive this expression, or if they derive it with a very, very high mathematics, which is of no use. But we are deriving it with respect to energy band diagram. You have seen in the PN junction, every single formula derivation we are doing with respect to energy band diagram only, okay? So Ni square by Nd e to the power Va by Vt. So what you are getting? Number of holes in n side at x equals to xn is coming out to be, what is Ni square by Nd? Number of holes in n side under equilibrium. Number of holes in n side under equilibrium. Number of holes in n side under equilibrium e to the power Va by Vt. You will remember this formula. How will you remember? No need to worry about that. I will tell you how to remember this formula. But as of now, you are just observing the final answers. And similar answer you can make, similar scenario or similar analysis you can do here as well at x equals to minus xp. That means at a p side. This you should be able to do on your own, right? So number of electrons at p side at x equals to minus xp, number of holes on p side at x equals to minus xp should be equals to ni square e to the power Va by Vt. So number of electrons on p side at x equals to minus xp, that I don't know, but number of holes on p side at x equals to minus xp is Na, that is equal to ni square e to the power Va by Vt. So ni square by Na, number of electrons on p side at x equals to minus xp, that would be ni square by Na e to the power Va by Vt. So number of electrons on p side at x equals to minus xp, that is coming out to be ni square by Na, that is your number of electrons on p side under equilibrium, e to the power Va by Vt. So these are your excess carrier that you are getting. Sorry, not excess carrier, these are your total electron concentration on p side at x equals to minus xp, total hole concentration on n side at x equals to minus xn, such that applied voltage is Va. Clearly understandable? Clearly understandable? Say yes or no, right? So let's write down the conclusion. What is the conclusion? So under forward bias, now I am making only minority carrier concentration. Okay, what I am making under forward bias, only minority carrier concentration I am making. So what is happening with minority carrier concentration, that I am making now. Okay, so from p side, holes are being injected here. So here I will get some concentration, and then I know that as I move into the length of n side, then eventually I will reach the equilibrium. So eventually I would reach the equilibrium. The equilibrium says that number of holes, we are talking about the minority carrier concentration. So number of holes in n side under equilibrium should have been Ni square by Nd. But here at xn, number of holes in n side at x equals to xn, that is coming out to be Pn naught e to the power Va by Vt. So this is the whole length. This is the whole number, right? What is your delta Pxn? Delta Pn xn I should write down. What is this? This is your excess holes in n side at x equals to xn because of applied potential Va, or because of Va. These are the total holes. What is this? Total holes. I need to find out the excess. So what that would be equivalent to? So this minus this, right? Pn naught e to the power Va by Vt. These are the total minus this. So that would be equivalent to Pn naught into 1 minus e to the power Va by Vt. Now what I am writing down, have some patience, look at it very carefully. What I am writing down? I am writing down Pnx. What does that mean? Profile of excess holes in n side with respect to x. Like as you move along the length, how the concentration of excess carrier concentration would change. Again, let me repeat the statement. As you move in the n side, how will the excess minority carrier concentration will change with respect to x? Excess holes, you see this word. So this much width, sorry, this not width, this much height. What is this much height? Sir, this much height is nothing but Pn naught into 1 minus e to the power Va by Vt. How do I write it down? I think I need to push it more aside. Okay. So, sir, this much height is nothing but Pn naught 1 minus e to the power Va by Vt. Okay. So, this is this much height. And that would decay down with respect to x. And how it will decay down? It will decay down exponentially. So, if your mathematics is good enough, you will be able to write down the expression, and that expression would be, sir, Pn naught into 1 minus Va by Vt. That is the concentration initially you are having, but it will decay down. It will eventually decay down, right? So, how it will decay down? So, e to the power minus x minus xn divided by Lp, diffusion length of holes, okay, plus Pn naught. Did you understand this equation? Did anyone understand this equation? This is only about the excess, no? So Pn naught is not required. Pn naught would become the total one. So did anyone understand this equation? What I am writing down? Profile of excess holes in n side with respect to x. That means, sir, whatever the part that has been generated here, this particular part will completely decay down, no, with respect to the length. So do you remember in electrical injection, what did we do? Sir, delta P was generated. So what we wrote down? Delta P naught 0 e to the power minus x by Lp. So there everything was happening at x equals to 0. Now here everything is happening at x equals to xn. Everything is happening at x equals to xn. So in place of writing down minus x by Lp, what I am writing down? Minus x minus xn by Lp. Whatever the excess part is there, that will be completely decayed down. Whatever the part that came from the P side, that will be completely gone, sir. Okay, if that will be completely gone, then what was generated at x equals to xn? Sir, this much was generated at x equals to xn. So that will be completely gone if you move for some distance in n-type semiconductor. So what was generated at x equals to xn? This was generated. And how it will decay? It will decay exponentially. So e to the power minus x by Lp. But here I will write down x minus xn, because at x equals to xn, this much part was there. But at x equals to infinity, this complete part would be gone. So this is your excess hole profile. Okay, excess holes profile in n-type semiconductor for PN junction. Similar thing you can write down for p-type semiconductor as well. I am leaving it up to you. I will add a page and I am leaving it up to you that you will be writing it down. Along with that, we will be solving a numerical as well. With respect to numerical, everything would be clear. Okay, so let's make the diagram here first. What will happen? Some electrons will come up here and they will diffuse. Again, I am using the word diffuse. They will recombine. Diffusion is different, right? Diffusion is the current. Diffusion current would come into action, no? Because you know that here there is more concentration and eventually at the equilibrium there will be lesser concentration. Because of this concentration difference, the current would set up, right? So we will see the current equation and everything, but eventually they are recombining. They are recombining with respect to the distance, right? So this is your P side. Why I wrote down Lp here? Because who are recombining? Holes are recombining, no? Holes are recombining, no? So I will write down the diffusion length of holes. Lp is the diffusion length of holes. You are writing down the equation for holes, right? Diffusion length of holes. So this equation is for holes. That's why Lp, right? Here I will write down Ln because I am writing down the equation for electrons, right? All clear? What will be the concentration here? Number of electrons on P side at x equals to minus xp. What that would be? So that would be equivalent to number of electrons on P side under equilibrium. Number of electrons on P side under equilibrium e to the power Va by Vt. So sir, this will be the concentration here. But what about the excess carrier concentration? What about the excess minority carrier concentration? So sir, if I look at the excess concentration, that means the excess would be, from this one I will subtract this much, so that would be NP naught. This I have written opposite. Okay, sorry guys, this is a big blunder. E to the power VA by VT minus 1. Okay, this is a very big blunder. Right. Because PN naught I am taking common, no? So here also NP naught we will take common, e to the power VA by VT minus 1. Right? And then they will be diffusing. So let's write down the excess excess electrons on P side at x equals to minus xp. That would be equivalent to excess I am writing down. So total, that would be this much minus equilibrium. So this would be your excess, right? And if I need to write down the expression with respect to simple distance, then what will happen? Whatever that has been generated, that will decay down exponentially. That will decay down exponentially. Divided by ln. How did I write down this equation? Because you know that in this equation, if I put x equals to minus infinity, that means this particular part should be equals to 0. So if you put x equals to minus infinity, e to the power minus infinity, that would be 0 only. And here if I put x equals to minus xp, so this particular part should throw e to the power 0, that should be 1. So this particular part should throw this much value. So it is throwing this much value only. So np naught e to the power va by vt minus 1. np naught e to the power va by vt minus 1 at x equals to 0. Sorry, at x equals to minus xp, this much should be thrown. And it is throwing this much value only. Okay, and at x equals to minus infinity, it should throw 0. So it is throwing 0 only. So in the examination, we will solve the numerical problem. With respect to the numerical problem, you will be able to understand how to apply these formula. So don't mug up these formula. Mathematics may look difficult, like it is not difficult. It may seem like, sir, a lot of formulas are there. Nothing, only one formula. If you remember this one, then your job is done. Or directly remember this one. Number of electrons or number of holes in n side at x equals to xn under forward bias, that is Pn naught e to the power Va by Vt. So whatever the equilibrium condition holes you will be getting, multiply with e to the power Va by Vt. And you know that, sir, Va would be positive. So e to the power something positive, that would be greater than 1 only. So this value will be increased. Right? And similar goes for other side as well. We will solve this question. So this question has been written 1, 2, 3. Try solving this fourth question as well. If someone is able to solve the fourth one, then he is a very, very good student. Okay, answers are written. Answers are completely written. Okay, try solving the fourth one. Try solving first, second, third as well. I will take a break and come back. You also drink some water. You revise whatever that we have studied, and then try solving this particular problem. What all things we need to find out? Compute the equilibrium minority hole concentration in the n side. Like if you are not able to compute this particular thing, then you need to worry, right? But you will be able to compute this one, right? Minority hole concentration. What that would be? Hole concentration on n side, that would be Pn naught. So what will be the answer for this one? The Pn naught would be Ni square by Nd. So Ni square 10 to the power 20 divided by Nd, that is 10 to the power 16. So answer is coming out to be, sir, 10 to the power 4 centimeter cube inverse, right? Next, what they are asking, under applied forward bias, the total hole concentration and the excess hole concentration at x equals to xn and at x equals to xn plus Lp by 2. Okay, so total and excess. So if we solve the second one, what it is saying, total hole concentration at x equals to xn. So total hole concentration on n side at x equals to xn under forward bias, what will happen? Sir, whatever the equilibrium we will get, total hole concentration on n side, whatever the equilibrium we will get, e to the power Va by Vt. It will be just increased by e to the power Va by Vt. So at the equilibrium you were expected to get e to 10 to the power 4, but it would become e to the power Va by Vt. What is Va? 0.3 divided by Vt would be 25.9. 0.3 divided by 0.0259. So what you are getting here? So you can see that this number has increased drastically. 1.072 into 10 to the power 9. So these many total holes we are having. Total holes on n side at x equals to xn under forward biased. So these are the total holes. 1.072 into 1.072 into 10 to the power 9 centimeter cube inverse. Now what about the excess holes? Excess holes at x equals to xn. What that would be? Sir, excess holes will be delta p xn. What that would be equivalent to? Total holes minus already that were present. So total holes were 1.072 into 10 to the power 9, and already that were present, that were PN naught. What were already present? 10 to the power 4 were already present. From here, what you will get? Nearly the same value only. Okay, and similar thing you need to do at xn plus LP by 2 as well, half of the diffusion length. So you know that how it will be diffusing. So similar thing you do at xn plus LP by 2 as well, and then you need to find out the current densities as well. So try doing it on your own. I will take a break and then I will come back. Okay. Yeah, welcome back. So did you try this question? So what we were finding out, total hole concentration we have find out, and excess hole concentration we have find out at x equals to xn, right? Now we need to find out the same thing at x equals to xn plus LP by 2. So what we need to do? We need to find out, let's find out excess hole concentration. Excess hole concentration, okay, in n side. So in n side, what is the excess hole concentration we are getting? So excess hole concentration in n side as a function of x we are writing down. So your excess hole concentration at x equals to xn, that is equals to Pn naught into e to the power Va by Vt minus 1, right? At x equals to xn, this is the scenario, but it will keep on reducing in this manner. So this expression we have already understood how to write down this particular expression. This is your excess hole concentration on n side, right, as a function of x, and this is the excess hole concentration at x equals to xn, right? So we have already seen how to write down this particular expression. What I need to find out? I need to find out the excess hole concentration at xn plus LP by 2. So excess hole concentration in n side at xn plus LP by 2, at xn plus LP by 2. So Pn naught e to the power Va by Vt minus 1 e to the power minus xn plus LP by 2. So xn plus LP by 2, so that would be here LP by 2 would come up divided by LP. So what will be the answer? Whatever the concentration I was having at whatever the excess concentration, this is the excess concentration. No? What this formula was equivalent to? This formula was equivalent to same thing, because Pn xn is Pn naught e to the power Va by Vt. So whatever the value that you are having here, just multiply with e to the power minus 1 by 2. So whatever the value I was having here, that was this much, and that multiply with e to the power minus 1 by 2. Okay. So this particular value multiply with e to the power 0.5. 0.5 plus minus 0.6. Okay, so what you are getting into 1.072. So 0.65, roughly around 0.65, and this would become 6.5 then. 6.51 into 10 to the power 8 centimeter cube inverse. So this is the excess hole concentration at xn plus Lp by 2 you are having. So this is the excess hole concentration. What will be the total hole concentration? So total hole concentration on n side at xn plus Lp by 2, that would be equivalent to Pn naught plus whatever the value that you get here, plus excess hole concentration in n side at xn plus Lp by 2. I hope if you are using your own pen, then you would be able to understand. If you are just looking at the screen that sir what you are writing down, sir what is this expression, then you will not be able to understand. Otherwise this thing is very straightforward. If you are not using your pen, if you are just looking at the screen without using the pen, then you will not be able to understand a single thing. Okay, it is not very difficult. Only the expression is looking difficult, only the math is looking difficult, but actually if you are using your own pen, you just know that from Pn naught the concentration has increased to Pn naught e to the power Va by Vt. So that much concentration has increased. Now that will decrease with the length. That's it. So Pn naught e to the power Va by Vt, that is the total concentration. So Pn naught e to the power Va by Vt minus Pn naught, that is the increased concentration. Now this increased concentration will decrease with the diffusion length. So e to the power minus x by Lp. But here x minus 0, in place of x minus 0 we are putting x minus xn. So very easily you will be able to find out these answers. Now you know that Pn naught is nothing but 10 to the power 4 only. So it will not make greater impact. Okay, so it is not making any greater impact here. Okay, so answer is 6.51 into 10 to the power 8 centimeter cube inverse only. Next, what all things we need to find out? Then we need to find out whole diffusion current density. So diffusion current density, very simple thing. Diffusion current density we need to find out. So let's make the diagram, otherwise you will not be able to understand. So whole diffusion current density we need to find out. That means we need to consider then n side only. Neutral n side, what is happening? Here some hole concentration came. Now you know that whatever the excess hole came, they will be diffusing. Right? Why they would be diffusing? Because here there will be more concentration and eventually this concentration is becoming Pn naught. Basically, eventually this concentration is Pn naught, but here the concentration is Pn naught e to the power Va by Vt. Right? This concentration is Pn naught e to the power Va by Vt and this concentration is Pn naught. That means there is a concentration gradient. There is some concentration gradient available and because of that you will get some current. That's for sure. Right? So what do I require? I require excess hole concentration on n side. How it is depending on x? So that is depending in this manner. E to the power minus x minus xn divided by Lp. Say yes or no. Like at least 4 to 5 times I have explained this particular formula. Basically, this is your excess hole concentration. Why I care about excess hole concentration only? Because what I need to find out now? What I need to find out? I need to find out diffusion current density. What is the formula of diffusion current density? Diffusion current density of holes on n side. Diffusion current density of excess holes on n side. This is what I need to find out. The formula is Q dp d by dx, and here what do you write down? What do you write down? Here you write down the concentration of holes with respect to x. That means concentration of holes in n side with respect to x. So what is that equivalent to? Q dp d by dx, concentration of holes in n side with respect to x. So that is equivalent to, this is the equilibrium value. This we will surely have, but along with that we had some excess value as well. If only equilibrium value was maintained, that means there was no current, because this will be a constant, this will be a uniform value. So till this point the differentiation would be 0. But because of that something is happening. Basically, previously what was the scenario? Under the equilibrium this was the scenario. This Pn naught was uniform, so this would throw 0 value. But now this is the scenario. Right? Now because of this delta Px, some current would come up, but I need to find out at x equals to xn, and I need to find out that x equals to xn plus Lp by 2. At 2 points they are asking at xn and xn plus Lp by 2. So what I need to find out? I just simply need to find out the slope, right? So diffusion current because of the holes on n side at x, that is coming out to be this much. And if I put the values q dp as it is, d by dx. Now what is the excess value we are having? Sir, excess value we are having is Pn naught is the equilibrium value, and then Pn naught is the equilibrium value, and e to the power Va by Vt minus 1. This much excess was set up, and then it is reduced down with the distance in this manner. Okay, so if you differentiate, what you are getting? This particular part is constant only, like this is not a function of x, so this particular part can come outside. This part is coming outside. Q dp Pn naught Lp e to the power Va by Vt, and negative sign is already outside. But if you remember one thing, when we write down the current for holes, we always use the negative sign here, right? Because in the direction where holes are diffusing, current would be in the same direction. So this particular thing would come out to be negative only. To compensate this negative sign, we use another negative sign. This thing we understood when we were studying about diffusion current, right? So we will use another negative sign here. So another negative sign is already going on. So now when you differentiate this, one negative sign would come up, and this negative sign and this negative sign would be settled down. Okay. So when I differentiate this one, 1 by Lp is coming outside, this 1 by Lp is coming outside, and here this particular thing we are getting. So this is the diffusion current density expression we are having. Now I can find out the diffusion current because of the excess holes in n side at x equals to xn, and then I can find out at xn plus Lp by 2 as well. Okay, and divided by Lp as well. Simply the differentiation I have done, nothing else. This constant part comes outside. Not constant, I should say uniform part comes outside, and then differentiation of e to the power minus x minus xn by Lp. So minus 1 by Lp will come outside, so minus minus will get cancelled out. So q dp Pn naught e to the power Va by Vt minus 1 divided by Lp, and differentiation of this one would be e to the power minus x minus xn divided by Lp only. Okay, well and good. So what we need to find out? We need to add a page. Do I have the page? Yes. So I have to add a page in a manner, and now I need to write down my diffusion current because of the holes at x equals to xn. That would be equivalent to, here if I put xn, it would be e to the power 0. So what you are getting? Q dp Pn naught. Look, mathematics may look difficult for once, but with time it will not look difficult if you are using your own pen. But if you are just looking at the screen, you will feel like that, sir, it is difficult only. So q dp Pn naught Lp e to the power Va by Vt, any value you can put, you will get the answer. So all the values would be given. You can put all the values, you will get the answer. The answer would come out to be 3.43 into 10 to the power minus 6 ampere per centimeter square. 3.43 microampere per centimeter square. 3.43 microampere per centimeter square. And then you need to write down diffusion current density because of holes at x equals to xn plus Lp by 2. So here you see xn plus Lp by 2. So xn will get cancelled out. Lp by 2 divided by Lp, that would be 1 by 2. So e to the power minus 1 by 2 will be multiplied. So whatever the answer that you are getting here, this answer will be multiplied with e to the power minus 1 by 2. Say yes or no? This complete thing will be copied and multiplied with e to the power minus 1 by 2. Right? So you guys will be getting confused. So better I write down in this manner only. So whatever the answer that you got here, that should be multiplied with e to the power minus 1 by 2. So 0.5 plus minus hour into 3.43. So we are getting 2.08, right? So 2.08 microampere per centimeter square. So this is the expression of current because of the holes we are getting. Expression of current because of the excess minority holes. So similar kind of concentration would be there towards the p side as well. Like everything we are calculating towards n side. So similar thing would be happening towards p side as well. Like here p side would also be there, but in this problem we are not caring much about the p side, but I'm just telling you the similar thing is happening towards p side as well, because it is the PN junction, no? So similar thing is happening here as well, right? At the equilibrium you would want NP naught, and here this is your NP naught e to the power VA by VT. The similar thing is happening here as well. There as well you will get these expressions, and you can see that with respect to the distance the current is reducing, right? When you are working on this particular graph, that means if I am working from xn to infinity, my current will reduce, and similarly here as well, if I go from minus xp to infinity, minus xp to minus infinity, the current is reducing, which is obvious as well because the slope is decreasing. Or what you can see that, sir, here there will be more number of holes, here there will be lesser number of holes, so that means this particular point will see the highest gradient. More number of holes here, very less number of holes, so this particular point will see the highest gradient. But if you are at xn plus lpy2, if you are somewhere here, then this will not see much of gradient, and here this will see minimum gradient. Why is that so? Because after a certain distance everything will be PN naught, PN naught, PN naught, PN naught only. What this guy would see? Sir, very high concentration than PN naught. This guy also will see high concentration than PN naught, but eventually what will happen? Sir, PN naught, PN naught, PN naught only. That means not much concentration gradient I would see. So as I move along the length, the concentration gradient is actually reducing, so current will also reduce. Okay, so all these points are very good conclusion. Okay, these numerical problems are good, along with that they are good conclusion as well, because we are going to derive the expression of current. Okay, we are going to derive the current expression in PN junction forward bias. So there all these expressions will be useful, right? So if you want to write down, let's just say you want to write down diffusion current density on n side, sorry, diffusion current density because of the excess electrons on p side at x equals to minus xp. What do you think, what answer you will be getting? So this I am leaving it up to you. This answer would be AQDN NP naught divided by ln e to the power VA by VT minus 1. What you will do? Sir, I will write down the excess electron concentration on p side. This is what I will write down. What that would be equivalent to, sir? NP naught e to the power VA by VT minus 1, and sir, this would be decreasing. This would be decreasing with the x plus xp divided by LP. Now what I need to do, sir, if I need to find out the current density because of the excess electrons on p side, if I need to write down this particular thing, then sir, q dn d by dx delta and px. Then sir, simply I need to differentiate it. So q dn np naught e to the power VA by VT minus 1 divided by, here ln would come, ln, and differentiation here would be e to the power x plus xp divided by ln. And when I put minus xp here, this part would become 1 only. So this is the answer I am getting. Q dn np naught divided by ln e to the power VA by VT minus 1. So derivation here only I did in rough manner. You can do in fair manner, or wherever you want to do it, you can do it. Okay. But another thing we need to calculate. Now this is an important problem. Okay, this is a good question. This can be asked in the examination. What they are asking? Assuming the n region is semi-infinite, that means n region is very large. So in the whole analysis, whenever we are doing the analysis of PN junction, we are always assuming that our PN junction is spread till infinity. This is what we are assuming. Like center is x equals to 0, but I never talked about that till what point we are going. Like this is my x equals to 0. I will have the depletion width, but till what point your n side is spread, till what point your p side is spread. So we will say that, sir, it is very long compared to what? Diffusion length actually. Very long compared to the diffusion length. Are you able to understand this point? What I am saying? This particular side is very long compared to the diffusion length, because you know that this is reducing, this concentration is reducing with the diffusion length only, right? If you calculate this particular value at x equals to xn plus 5 lp, your answer would be nearly 0. Your answer would be nearly 0 only. You put here xn plus 5 lp, what you will get? E to the power minus 5. E to the power minus 5 is nearly 0. Okay, so if my whole diffusion length is lp, then this distance, this whole distance is at least 5 lp. Okay, it would be more than that. Are you able to understand this point? What is the meaning of infinite length? Infinite length is, this length is large enough so that whatever the excess holes or whatever the excess electrons that we are getting, they will be diffused in a good enough manner, right? They will be diffused in a good enough manner, and we will get the equilibrium condition very easily. So the length is infinite only. Till this point infinite, and till this point as well infinite. On both of the side, till infinity it is spread. So this will be plus infinity, this will be minus infinity. What you are asked to find out? Compute that total injected charge per unit area in the n side. Total injected charge per unit area in the n side from the p region. So from p, how much charge has been injected towards the n side? This is what we need to find out. So from p, what we are injecting? We are injecting holes, right? From the p side, what we are injecting? We are injecting holes, and each hole will have a charge of q. So how much charge we are injecting? We are injecting q into this much charge. How many holes we are injecting? We are injecting the excess holes. That means number of excess holes in n side, right? So these many holes we are injecting. How many holes we are injecting? So if I integrate this from 0 to infinity, then these are the total number of holes we are injecting. Are you able to understand this point? Delta Pn x, what it would represent? It would represent the concentration of holes with respect to x. Concentration of injected holes with respect to x. Let me write down the theory, then you will be able to understand. Concentration of injected holes from p side to n side, from p region to n region, that is delta p nx, right? That goes like this. Like you need to find out only the injected ones. These are the already present ones. Like Pn naught was already present. Injected ones are this much. So at x equals to 0, this much, and then with respect to distance, it is reducing only. Are you able to understand this point? And this is per centimeter cube. Per centimeter. I should not say per centimeter cube. If I am writing down centimeter cube inverse, that means it is per centimeter cube only, right? And if I need to find out the total injected holes per unit area, total injected holes per unit area, what that would be? So that would be equivalent to, you integrate it from xn to infinity, delta pnx dot dx. From xn to infinity, how many holes are being injected? So these many holes are being injected, no? From xn to infinity. Say yes or no. Do you agree to this point or not? From xn to infinity, these many holes are injected. So what I would do? Basically, this is having a unit of a centimeter cube inverse. Now you are multiplying with x. That means it will have a unit of these many holes per centimeter square. And if I need to find out the charge, so total charge injected, I will simply multiply with Q from xn to infinity. Say yes or no. So what that would be? Sir, Q xn to infinity. This was Pn naught e to the power Va by Vt minus 1 e to the power minus x minus xn divided by Lp dot dx. Okay, so this would come out to be Q into Pn naught into Lp e to the power Va by Vt minus 1. Can you integrate this? Very easily I can integrate. E to the power minus x minus xn by Lp. So 1 by Lp would come upward. So it would become Lp. So Q Pn naught and e to the power Va by Vt minus 1, that is already a constant. Or you can say that is already uniform, that goes outside, and from here I get Lp. So this is the answer we are getting. So this is not written in a very good manner. I will write down in a much better manner. So answer we are getting Q multiply with Pn naught number of access holes, this we already know, e to the power Va by Vt minus 1 multiply with Lp. So you can do this calculation. We are having all the values. So Pn naught e to the power Va by Vt, I guess this value we have already calculated. Pn naught e to the power Va by Vt, this is this much value, 1.7072 into 10 to the power 9. 1.072 1.072 into 10 to the power 9 into diffusion length would have been given 5 micrometer. 5 micrometer, but everything is going into centimeter, so 10 to the power minus 4, right? And then what I require, this much I already know, Lp value I can put here, and then I simply need to do 1.6 into 10 to the power minus 19. So this much calculation I need to do. So 1.6 into 1.072 into 5. So 8.576 and then 10 to the power minus 14. So this much, 8.576. Yeah. What this is written? Yeah. So here it is simple formula is written here. So that I wanted to hide. So 8.576 into 10 to the power minus 14. So you can put the values here. You will get the answer same as given in the answer sheet. Okay. So whatever the answer that has been given here, the same answer you will be getting here. So 8.576 into 10 to the power minus 14, this much coulomb per centimeter square. Okay, this much charge per unit area, 8.576 into 10 to the power minus 14 charge per unit area. They are not asking the number of holes. If they were asking only the number of holes, then this would be the answer. Number of holes injected per unit area, this would be the answer. If they are asking only about the number of holes, they are asking about the charge, then I will simply multiply 1.6 into 10 to the power minus 19. A lot of people in this question, what mistake they would have done? They would have only calculated this particular concentration, right? They would say that, sir, these many holes are injected. These many holes are injected. These many holes are available at x equals to 0. Oh, sorry, at x equals to xn. How many total holes are injected? This much total holes are injected, no? So you need to take the integration. Are you able to understand this point? Okay. And this is per unit volume. You need to find out, like basically per unit volume, these many holes are available at this particular point. I need to find out the total holes per unit area. So what I would do, I would write down the expression of this. What is this expression? So it is delta PNX. So this expression I will write down, and then I will integrate it with respect to x. That means I will find out the total excess hole concentration per unit area. If you are listening to the words very carefully, you will be able to understand what I am saying. Total excess hole concentration per unit area I need to find out. So this particular integration I need to perform. Delta PNX dot dx from xn to infinity. And if I multiply with the charge, then this is the answer I am getting. Surely it is coming in your gate examination in near future. 101%. Like what I feel is that in 2026 only it is coming. It might come in 26 or 27. Till this date, they never asked about the total charge. Okay. They have asked this question. This one they have asked. They did not even ask this one. So either they can ask first this one, or they can simply go towards this one. Sir, why did you pick this particular question? This particular question I picked to explain the next topic. So our next topic is ideal diode current equation for the forward bias. Okay. So to explain the current equation, I took this particular example. So here you can see this expression will be my matter of concern. This expression will be my matter of concern. And these two values which you can see, the current is reducing. That will be the matter of concern. Just 1 second, I will drink some water. Okay, then we will derive the ideal diode current equation. So I am just making this diagram. Now I need to make the diagram of current. So we will make that diagram, but just 1 second. Yeah, so we need to study about the current, right? So now we need to derive the expression of current, like how much current is flowing in the PN junction diode. Diode means PN junction only. Okay, don't get confused. It is simply PN junction only. So how much current is flowing in the device? Whatever the device that we are studying, how much current is flowing there, that we need to find out. Here one approximation I will take, that nothing is happening inside the depletion region. What is that approximation? What I am saying, nothing is happening inside the depletion region. Under equilibrium, what was the condition inside the depletion region? Sir, inside the depletion region, this was the condition under equilibrium. Sir, when you applied the forward bias, this is something happened. That means inside the depletion region, listen to me very carefully, okay? Inside the depletion region, the charge carriers got increased when I applied the forward bias. Now there is a thing that device would always try to maintain its equilibrium. So in any semiconductor device, always there will be recombination and generation process going on. Okay, on brief only I am telling, we will discuss in detail as well. So what I am saying, when your PN junction, this was my PN junction, this was under equilibrium. Okay, this was under equilibrium, then N into P equals to Ni square was applicable. That means these many number of holes and these many number of electrons I was having inside the depletion region. I am only caring about depletion region. Now when I applied the forward bias, inside the depletion region, suddenly more charge carriers came into action. Because inside the depletion region, N into P equals to Ni square e to the power Va by Vt is coming, then you know that Va value will be some positive value, Vt value will be some positive value, so this value will increase. That means inside the depletion region, the charge carrier got increased. Now the depletion region will oppose the increase of charge carrier, because every semiconductor device or every material will try to maintain its equilibrium. So depletion region would say that, this depletion width would say that you have increased the number of charge carriers in me. You have increased the number of charge carriers in me. Now what I will do, I will kill those charge carriers. That means inside the depletion region, some recombination will start taking place. Did you understand the statement? Sir, how this recombination came into action now? Actually, we ignored this particular thing. What we are ignoring, that I am telling. That inside, on top level, what you can understand, that inside the depletion region, some generation recombination would be happening. And that generation recombination we are ignoring. Basically, nothing is happening inside the depletion region. This is our assumption when we derive the ideal diode current equation. We will also see non-ideal diode current equation. There we will take up this assumption that we have taken now. So this ignorance that we have done, that we will take up when we study non-ideal diode. So as of now, what you need to understand that sir, nothing is happening inside the depletion region. Depletion region will do whatever that I ask them to do. Okay, so this point I will explain in more detail once we study non-ideal diode. In this lecture only we are going to study that. Okay, so as of now you need to understand that depletion region will do whatever you ask him to do. That's it. Okay, so this guy will do whatever you ask him to do. That's it. This is the assumption that you are making as of now. Now just tell me one thing. Can I find out the current here? I know that what is happening in a PN junction when it is forward biased. What is happening? A lot of holes are coming from here to here, and a lot of electrons are coming from here to here. And you can see that what will be this concentration? So this concentration is nothing but NP naught a to the power VA by VT. And sir, VA by VT. And sir, this concentration is PN naught a to the power VA by VT. Okay. Now because of the concentration gradient, diffusion current would flow, because here there are more number of holes, here there are lesser number of holes, and because of that diffusion current would flow. How much diffusion current would flow, that we already know. But I know one thing as well. What is that? That sir, as I go along the distance, like from xn to, if I go to xn plus LP by 2, or from xn to xn plus LP I go, or xn plus 2 LP I go. So as I move along the n side, the amount of current will reduce. Say yes or no? Do you agree to this point? So here whatever the current that I am getting, let's just say here at this point this much current I am getting, which is A, like this is the current density, no? So if you find out the current, then you will multiply with the area as well. So AQ dP PN naught by LP e to the power VA by VT, this much current you are getting because of the excess holes, right? Here, let's show it here. So this much current you are getting because of the excess holes here. Some current you are getting, that is given as I, because of the holes you are getting in n side at x equals to xn. Similarly, here as well you will be getting some current. You will be getting current I because of the excess electrons in p side at x equals to minus xp. Say yes or no? This current will also decrease with length. This current will also decrease with length. You can see the expression, no? Where was the expression? This was the expression. That if xn increases, like if x increases, x will go from xn to infinity, then this particular value will decrease. That means this current density would decrease. If current density is decreasing, that means current is also decreasing. So this current would decrease. And eventually this current would become 0 only. Do you agree to this point? And here also the same scenario would be happening. This current would decrease and eventually this current would become 0. Okay. Now I know one thing. What do I know? That nothing is happening inside the depletion region. So whatever that is happening as the edge of depletion, the same thing will happen inside the depletion region as well. Let me repeat my statement again. What I am saying, whatever that is happening at the edge of depletion, I told you there is no recombination, there is no generation, there is no process going on inside the depletion region. That means whatever the current that you are getting here, the same current you will be getting inside the depletion region as well. The same current I will be getting inside the depletion region as well. So this was the current because of the holes. And here as well I will be getting the same current because of the excess electrons. Are you able to understand this or not? Like this is my PN junction diode. Okay. This is my PN junction diode. Now here because of these excess holes, here I am getting some current. And because of these excess electrons are moving in this direction. That means current would be in this direction. These excess holes are moving in this direction. These excess hole will be diffusing in this direction. That means their current would also be in this direction. These excess electrons are diffusing in this direction. That means their current would be in this direction. That means direction of current is same. In both of the cases, direction of current is same only, right? This is the direction of current. So here as well, this is the direction of current. So direction of current is the same. No issue about the direction of current. Now at this point, I could know that, sir, this amount of current is flowing. Let's just say this is I1. Now I said that whatever that is happening at the edge of depletion, the same current I1 would have been flowing inside the depletion region as well. Along with that, on the edge of this depletion region, on the edge of depletion region towards the P side, I know that some current I2 is flowing. So the same I2 current would be flowing inside the depletion region as well. The direction of I2 is this much. So inside the depletion region, you are getting two current component. What is the first current component? That is current because of the excess hole inside the depletion region, or better I should say current because of the excess holes in n region at x equals to xn, plus current because of the excess electrons in p region at x equals to minus xp. So this current has been carried here, this current has been carried here, and whatever the current that you are getting two current components in the depletion region. Addition of both of the current will be your total current. Addition of both of the currents will be my total current. So this will be my total current that I am getting. So inside the depletion region, this is the total current I get. Are you able to understand this point? Shall I explain it once more? If you are listening to me, if you are listening to me very carefully, then only you will be able to understand. Otherwise, I could have ignored this derivation. But if I ignore this derivation, you are not learning EDC then. Okay, EDC can be taught on a very surface level as well. It can be taught in this depth as well. I don't know, like I might be reflecting a lot of students because of this much of depth, or it might happen that a lot of people would be impressed by this much of depth. So it depends on the what kind of students I am teaching. Okay. So what I am saying, at x equals to xn, there are holes have been injected from p side to n side. So a lot of holes have been injected from p side to n side. Because of the concentration gradient, there is some current, and that current will reduce down with the distance. Similar thing would be happening here as well. But I know one thing, nothing is happening inside the depletion region. That means whatever the current that I am getting at x equals to xn, the same current I can carry inside the depletion region, and whatever the current that I am getting at x equals to minus xp, the same current I can carry inside the depletion region. That means my total current inside the depletion region, let's forget about this total ideal current, forget about it. Total current inside the depletion region, that is coming out to be my current because of the excess holes in n side at x equals to xn, plus current because of the excess electrons on p side at x equals to minus xp. Addition of both of them will be equals to your total current. Okay. Now can I write down this particular expression? Yes, I can write down this particular expression. What that would be? So this particular expression you have already written. Here just you multiply with area, then you will get the expression AQ dP PN naught divided by LP e to the power VA by VT minus 1. So AQ dP PN naught divided by LP e to the power VA by VT minus 1. And here you will be getting AQ dN NP naught divided by Ln e to the power VA by VT minus 1. Okay. Like here only we wrote down the expression, no? AQ dN NP naught divided by Ln e to the power VA by VT minus 1. Are you able to understand this total current? This is the total current that you are getting. Now someone will have a doubt, and I can understand that doubt. What doubt you are having? That sir, this is your PN junction, right? You are saying that sir, inside the depletion region I current is flowing. Inside the depletion region I current is flowing. But everything is connected in series, no? Everything is connected in series. So here if I current is flowing, so here also I current should flow, and here also I current should flow. That means inside the depletion region, if I find out the current, that current would be my total current only. and that total current would be equivalent to my ideal diode current. So this current is nothing but your ideal diode current only. Now the doubt would be that, sir, here because of the diffusion, because concentration gradient is getting lesser, the current will reduce. So sir, if the current is reducing, then how you can say this I total will be equivalent to this much? Because I total is already IPN plus INP, and here the current is reducing. So how will you make sure that, sir, this particular part remains constant or this particular part remains uniform? Because it is pretty obvious, no? It is very, very obvious that total current, whatever the current that you are getting here, the same current you should get here as well, and the same current you should be getting on the P side as well. So what does that mean? That means there has to be some other current component as well, which is making sure that if this current is reducing, then there would be some other current component which would make sure that this particular part get increased, and here this particular part also get increased. So basically there is one more current component. There is one more current component which is making sure that the addition of these two guys always remain uniform. Like this added with this one will be this much only. Now what is this current? From where this current came into action? Think about it. Pause the video, and what is that other current which is making sure that the total current remains uniform? It has to be uniform because it is basic law. It is basic Kirchhoff law that if I current is flowing here and it is only one device, then I current has to flow here as well. I current has to flow here as well. From where this current came into action? Think about it. We applied VA. Most of the potential got here, VF, but some potential got here as well, no? Let's call this potential as VS. Some potential got here as well. This potential is VS. Although this VS is very low, but here a lot of electrons are present. Here a lot of holes are present. And how much current an electron can drive? J equals to sigma E, N Q mu E. Sir, E is very less. The potential that you are dropping here, that is very less, sir, but N is very large, no? So they can also take up the sufficient amount of current. Say yes or no? Sir, E is very low, but N is decent enough, no? N is 10 to the power 16 doping you have done. So even if this very low E and this is sufficient enough N, they will make up the current, and they would make sure that whatever the decrease in diffusion we are having, the same increase in the drift we are having. So I told you this will be your drift current. So I told you in the forward bias, drift and diffusion, both current components are there. So this was your hole diffusion, excess hole diffusion. If I write down in a quicker manner, in a good manner, so this was your excess hole diffusion. Excess hole diffusion current. What is this? This is my majority electrons drift current. Is that understandable to you? What this would be? This would be my excess electron diffusion current. And what this would be? This would be my majority hole drift current. So drift plus diffusion, the total current would remain uniform. So from where this current came into action? This current came into action because some potential was being dropped across the neutral region as well. If this was my PN, it's not that everything is being taken by depletion width. Most of the part is taken by depletion width, most of the part is taken by depletion region, but some part is still there, no? And that some part and good enough number of electrons, that some part and good enough number of holes, they would make up a good amount of current. Okay, so applied electric field was in this direction, Applied electric field was in this direction, so holes moved in this direction, electrons moved in the opposite direction, and because of that some current flow and some current flows. So this was the drift current, this was also the drift current. These two drift current combined, they made the total current. Is that understandable to you? Is this plot understandable to you? Okay, if you are going to give a very good interview in devices, then this is how you need to explain the things. I know how these topics are taught. Okay, I have seen the lectures, I have seen everyone's lecture, a lot of gods are there. I have seen the lectures of gods as well. I have seen the lectures of human beings as well. So, are you able to connect the dots? Is it being too much? And how did you find out the current expression? Like here it would be difficult for us to find out, no? Like here the slope is continuously decreasing, so how much this will increase, I don't know. So what I did, at the boundary at x equals to xn, I will always be interested in the edge of depletion. So at the edge of depletion, I can find out the current expression. I know that the same current will be carried in the depletion region. At x equals to minus xp, I can find out the current expression. I know that the same current will be carried inside the depletion region. Addition of both will be my total current. Total current inside the depletion region, that has to be the total current only. So this is my ideal diode current. Ideal diode current. Now from here what you can do? E to the power Va by Vt minus 1 you can take common. So what you will be getting? Aq dp Pn naught. Just have the practice of writing down. Aq dp Pn naught. How do I remember? Aq dp Pn naught. Pn naught divided by Lp. So everything goes for P side. Everything goes for N side. Not for P side. I should not say P side. This is actually N side. The whole current, because of the excess holes on N side. Current because what is this? IPN. Current because of the excess holes on N side at x equals to xn. Current because of the excess electrons on P side at x equals to minus xp. Right? So Aq dp Pn naught divided by Lp plus Aq dn Np naught divided by Ln. So this part one side and this part one side, e to the power Va by Vt minus 1. Okay. Now this part can be like A is a constant, Q is a constant, dp is a constant, Lp is a constant, Pn naught is a constant. So this can be put by A. Like I should not say constant, this will depend on the device parameter. Like Pn naught will depend on device, Np naught will, what is Pn naught? Pn naught is whole concentration on N side under equilibrium. Right? So this can be defined by the doping. I am having a silicon, N side I have done the doping of Nd equals to 10 to the power 16 and Ni equals to 10 to the power 10. Then I know that my whole concentration on N side under equilibrium will be 10 to the power 4. So this will depend on the doping or the type of semiconductor that you are using. So this is your device parameter. dp, what is that? Diffusivity of holes, that is also a device parameter. Diffusion length of hole, device parameter. dn, ln, all these are device parameters, right? Device parameter, or you could better you say it is your semiconductor parameter, which kind of semiconductor you are using. So can I put it as simple I naught only? Yes. So this equation we are getting I naught Va by Vt minus 1. So this is your I total. So this is my ideal diode current equation, that is coming out to be I naught e to the power I naught e to the power Va by Vt minus 1. Okay, this is the ideal diode current equation in forward bias you are getting. Forward bias, forward biased. Okay, so usually people will simply write down this equation and then they will say what is I naught. So I naught also you need to remember. What is I naught? I naught is known as reverse saturation current. Reverse saturation current. This is just the name. Don't feel that sir it is coming in the reverse bias, nothing like that. It is simply a name. Reverse saturation current. Just consider this is a name. My name is Ram Kumar, so it is Ram Kumar. Would no meaning. It is simply a name. Doesn't mean that it is coming in reverse bias, nothing. It is forward bias. In forward bias as well, this reverse saturation current is coming. So simply a name. Okay, what is the value of this much? You should be able to write down in a quicker manner, sir. AQ dp PN naught, just build the practice, you will be able to write it down, divided by LP plus AQ DN NP naught divided by Ln. So this is how you should be able to write it down. Okay. Now this particular point, let's verify this particular point by more detail. What point? That as we go along the distance, the diffusion current would go down. The diffusion current would become 0. But there will be some electric field that would make sure that the total current still remains the uniform. That means whatever the number that we are getting here, that always remains the uniform. So let's solve a particular example. With respect to this example, a lot of concepts will be clear. Yeah, sorry for the interruption, guys. Actually, the question that has been already written, that had some problem. Okay, so when I was explaining this particular question, I realized that the data was not correct. So now the data has been correct. Okay, so this is a very important question. Actually, I would say very important question, and it is given in the Niemann as well. And from Niemann, I have told you again and again, every time in the gate examination, questions are framed from Niemann only, and it would be coming from there. Okay, although this is not how it is framed there, it is framed in different manner, but here I have framed it in exam oriented manner. Okay, in textbook you would see that questions are framed to explain, but here we are framing it in an exam oriented manner. So if this question is coming in front of your screen, then 99.99% aspirant will not be able to think what they are asking, right? What all things are given? PN junction fabricated, this much long silicon wafer is there. So let's try understanding one by one what the question is saying. So there is a silicon wafer we are having. Okay, from that silicon wafer, what you are making a PN junction. The length of that silicon wafer is 500 micrometer, and the metallurgical junction is at x equals to 0. That means this length will be 250 micrometer, and this length will be minus 250 micrometer, right? So this is your silicon. Now what you are doing that this is my p side. If I say this is my p side and this is my n side, then p side you are doping with acceptor atoms of 10 to the power 16, and this side you are doping with donor atom of 10 to the power 16 centimeter cube inverse. This is what you are doing, right? Intrinsic carrier concentration is already given, carrier lifetimes are given, diffusivity is given, mobility of electron is given, the diode is operating at 300 Kelvin, applied forward bias is there, forward bias you are applying. Okay, forward bias you are applying, that means p side is connected with positive, n side is connected with negative. So applied forward bias is there. 0.65. what you need to find out? You need to find out the electric field at a point 150 micrometer away from the metallurgical junction. So here at this particular point you need to find out the electric field. So those who have studied the topic, they would realize that somehow it is related with this particular diagram. Why is that so? Because they are asking electric field very far away from the junction. Like this is the junction, then what will happen? Sir, I will have some depletion width as well. Sir, some xn value I will have. Now from the xn as well, this will be very far away. That's pretty sure. Like I don't need to find out the depletion width. 150 micrometer from the junction, 150 micrometer away. Let's find out, first let's find out the diffusion length of holes. What will happen? From p side, holes will come into action. Now a lot of holes will be here. A lot of holes will come into action here. But with respect to the distance, they will be recombining. That means as you walk along the distance, at x equals to xn, there will be a lot of holes. But as you walk along the distance, the concentration of excess holes will go down. That means the current will also go down. Which current? The current because of the diffusion. Are you able to understand this point? The current because of the diffusion, here it will be very high. But I know that I have seen the plot. The concentration keep on decaying. If concentration gradient keeps on decaying, like here the gradient was maximum, but here the gradient became very less. If the concentration gradient keeps on decaying, the current because of the diffusion keeps on decaying. That means which current would be playing more role now? The drift current would be playing more role, and from that drift current you can get the value of electric field. That means my first task would be that first I would be able to find out my total current. If I am able to find out the total current, then I would know that here whatever the total current that I am getting, that total current would be mainly because of the drift of majority electrons. I am having the value of ND as well. I am having the value of mu n as well. I know the value of Q as well. From there, I can get the electric field. So if this much is clicking to you in the examination, then you are already brilliant. Okay, even AIR1, I don't think he will be able to solve this kind of questions if it is coming directly in the examination hall. Like it would not click like PN junction is given electric field at 150 micrometer away. What they are asking directly, it would not click to you, right? Forward bias is also there. So all these things will be very rare to click, right? But if you think deeply what they are asking, then it would be able to click. So let's first find out that diffusion length, because based on the diffusion length, I would be able to comment whether the diffusion current would be 0 or not. Because what is my diffusion current? Diffusion current, what was the diffusion current I was getting? Diffusion current I was getting, that expression was this much. This was the expression. So I know that at x equals to xn plus 5 LP. Nearly at xn plus 5 LP, what will happen? This particular part would nearly go down to 0. That means your diffusion current, because of the excess holes in n side, would become 0 ampere per centimeter square, right? That means the effect of diffusion current will decay down nearly at 5 LP. It would become nearly 0 at 3 LP only. I hope this much basics you know from your network analysis, right? At 5 tau, the transient response completely decays down. So it's like a transient response only, no? Here there is maximum current and the current is decaying down. So at 5 LP, the current will nearly decay down. Okay. So the component of diffusion current would be nearly decaying down at 5 LP. So first I am interested in finding out in diffusion length of holes. What that would be equivalent to? This formula I hope you remember. Okay. So what is dP? dP is 10 and what is tau p? That is 0.5. So 5 micro you are getting, right? And every calculation is going in centimeter, so this would be in centimeter. Whatever the answer that you get, that would be in centimeter. So as far as I remember, some 22 point something answer we will be getting. So 5 under root, yeah, 22.3 micrometer. 22.3 micrometer. When you solve it completely, under root, 10 to the power minus 3 will come outward. Under root 5 is 2.23. Then 10 to the power minus 3 into 10 to the power minus 2, what that would be 10 to the power minus 5. Then it would become 22.3 micrometer. So this is my diffusion length. And they are asking 150 micrometer away from the junction. From the junction, 150 micrometer away. Now, sir, there would be some xn as well. Like first, I need to go from 0 to xn, and from xn, it should be 5 LP away. So you don't need to find out this xn. It is almost sure that you are applying a very high forward bias as well, and you know that in forward bias, the depletion width is also very small. So don't waste your time in finding out the depletion width. Like this width will be very, very lesser. This width is already very lesser, and from here, how much away you are? 150 micrometer. So it is much more than 5 LP. What will be the value of 5 LP? If you multiply with 5, what you will be getting? 5 LP would be nearly, or 5 LP is nearly 111.8 micrometer. So 111.8 micrometer, then some distance, this would be at 150 micrometer. What I mean to say is that the current, because of the excess holes in n side at 150 micrometer would be equals to 0. This is the diffusion component I am writing down. Diffusion current. That would be 0 for sure. That means whatever the total current that you are getting here, this I total, whatever that you are getting, that is because of the drift of majority electrons. Say yes or no. So what that would be equivalent to? Sir, that would be equivalent to J equals to sigma E. J equals to sigma E. Sigma would be N Q mu N E and multiply with area as well. So this would be your I total equivalent to. Say yes or no. Right? I have the value of N. Yes. I have the value of Q. Yes. What will be N? N will be equals to ND only. that is 10 to the power 16 centimeter cube inverse. I have the value of Q, I have the value of mu1, I need to find out the value of E. Area, somehow it will cancel out with the current, because what will be my total current? Total current will be the current that is flowing in my PN junction. So PN junction total ideal current. So this current will be equivalent to whatever the current that is flowing inside your depletion width. So whatever the total current that has been flowing here, the same current I will be getting, no? So how much current is flowing inside the depletion width? So this current I already remember. So this current is equivalent to I naught e to the power VA by VT minus 1. And sir, what is the value of I naught? So that is equivalent to AQ dP PN naught by LP plus AQ DN NP naught by Ln, this particular part, and this will be multiplied with e to the power VA by VT minus 1. So I will find out this particular expression and my job would be done. So A I am keeping outside, Q also I will keep outside because A and Q can get cancelled out. Rest all the part I will keep inside. So what is the value of dP? dP is 10 and this is 25. So dP is 10. What is the value of PN naught? Na equals to Nd is given as 10 to the power 16. So number of electrons in p side under equilibrium would be equals to number of holes in n side under equilibrium. That would be equals to 10 to the power 4. No, intrinsic carrier concentration is 1.5. So that would be equals to 2.25 into 10 to the power 4. So this would come out to be what I am applying. I am only applying simple mass action law, right? So mass action law will simply say it would be 2.25 into 10 to the power 4. Okay, how did I get it? It's up to you. At least till this point you should be able to write down this much of things, right? So this would be 2.25 into 10 to the power 4 divided by LP. What is the value of LP I was getting? 22.3 micrometer. Okay, I don't think this answer would be correct because the values are different now, no? I guess, who knows? Let's see. Plus. So this thing is going in centimeter. This thing is also going in centimeter. So this also I should write down in centimeter only. So 22.3 10 to the power minus 4. 22.3 10 to the power minus 4 centimeter. So that's why I am writing down 22.3 10 to the power minus 4. Because dP is also in centimeter. This is also in centimeter. PN naught also in centimeter. This will also be in centimeter. Now what about DN? DN is, what is the value of DN? DN is 25. 25 into 2.25 into 10 to the power 4 divided by, what is the value of Ln? Ln will be Dn to 1. So what is the value of Dn? Dn is 25 and what is the value of to 1? The same. $35.35. It would come out to be 35.35 micrometer, right? This was coming out to be 22.3. This will come out to be 35.35 micrometer. 35.35 micrometer. And this part will be multiplied with e to the power VA by VT minus 1. VA is 0.65. VT value did they mention? It is not mentioned. It should have been mentioned actually. Okay. Why it should have been mentioned? Because VT is in exponential, no? Like 25 millivolt and 26 millivolt. Sometimes we can put the value of VT 25 millivolt. Sometimes we can put the value of VT 26 millivolt. They can make huge difference because it is in the exponential, right? So if VT is in the exponential, they should have given the value. We will take the exact one. More exact is 0.0259. So 0.0259 we are taking. Okay, but it would be given in the examination. So always see, because in the exponential VT can play important role, right? Now this would be equivalent to what? This would be equivalent to Nd into Q into mu n into E into area. So A and A is getting cancelled out, Q and Q will be getting cancelled out. What will be the value of my electric field? So you solve this particular thing and divide by Nd into mu n. You will get the answer. So let's try solving this particular thing now. So 10 to the power 8, 10 to the power 8 I will get. So 22.5 divided by 22.3. So it is nearly 1.00 only you are getting. And here 25 into 2.25 divided by 35.35 plus 1. So 2.59. So this particular part is coming out to be 2.59 into 10 to the power 8. What about this particular part? So 0.65 divided by 0.0259 e to the power minus 1. So this is coming out to be 7.93 into 10 to the power 10 into 2.59. So 2.05 into 10 to the power 11 into 8. So 2.05 into 10 to the power 19. 2.05 into 10 to the power 19. This is what we are getting. Now it should be divided by Nd into mu n. Nd into mu n. What is the value of Nd? That is 10 to the power 16 divided by mu n, that is 1350. Right? Mu n is given as 1350. So 2.05 divided by 1.3. 1.51. So yeah, nearly around 1.51 volt per centimeter we are getting. So when you solve from here, the electric field will come out to be 1.51 volt per centimeter. This is the electric field we are getting. So what did you understand? Why did I pick this question? I picked this question because I wanted to tell you one thing, that this length was 500 micrometer, right? This length was 500 micrometer. And how much bias did you apply? I gave it a bias of 0.65. Right? I gave it a bias of 0.65 volt. That means what was my E external? What was the total external field I applied? 0.65 I applied over the length of 500 micrometer. So can I write it down as 500 into 10 to the power minus 4 centimeter? So this much volt per centimeter I applied. How much is it? 5 into 10 to the power minus 2. So it is 65. So it is 12 volt per centimeter. Or 13. Right? Yeah, it is 13 volt per centimeter. So external field that you have applied, that is 13 volt per centimeter. Out of this, only 1.51 volt per centimeter has been found out at 100 micrometer. What does that mean? That means most of the external electric field has been dropped across your depletion width only. Is that clear what I am saying? Or shall we find out that how much basically there will be a depletion width as well, no? There will be some depletion width as well. Right? So across the depletion width also there would be some electric field. So how much electric field has been developed across the depletion width, that I don't know. But total external electric field was 13 volt per centimeter. This was your total external electric field. Out of this, at this particular distance, like very much away from the junction, 150 micrometer away from the junction, at 150 micrometer away from the junction, at some distance, your electric field is actually very less. That field is roughly around 1.51 volt per centimeter only, which is much lesser than whatever that you applied. So what I said, most of the potential is dropped across your depletion width, or most of the potential will be dropped in that depletion region, but some potential will surely be dropped across your neutral region as well. So this was your neutral N region. So did you understand why I picked this question? What do you understand from this particular question? First thing is that it is given in Niemann, so they can surely ask you electric field in this case. So this kind of question they would set up. What I feel is that they would not ask you to calculate this particular thing. They would give the forward current. Forward current you need to equate to NQ mu n epsilon, NQ mu n electric field into A. This is what they would be expecting. This is what I think, because this calculation would be a bit complex. Okay, so they would give the value of forward current. Then they would want to see, they would give the diffusion length as well. From there, they would want to see that are you able to understand that diffusion component is going down? What does that mean? That means drift component is coming into action. So that drift component would drive the current now. So we were actually calculating our current here. So I know that when we have reached till this point, here my diffusion component has nearly gone down to 0. So whatever the current that I am getting, the current I am getting from drift only. So here my total current would be nearly equals to the drift current only. And if they are nearly equal, that means I can equate them, and from there I can get the value of electric field. So in the forward bias PN junction, drift and diffusion, both components are there. Okay. And this drift current is flowing because of the majority carriers that are available in your, where they are available, majority carriers which are available in the neutral region. Although there is very less electric field, still that electric field is good enough to drive the current. And in the whole setup, the current will always be uniform. So did you understand the whole derivation? Did you understand the whole meaning of everything that we have discussed till this point? Okay. I guess there is conclusion only. Yeah. So this is your reverse saturation current I have written down. What was your total current? Total ideal current was I naught e to the power VA by VT minus 1. This was the ideal current in the diode I was getting. I naught e to the power VA by VT minus 1. Out of that, this is my reverse saturation current. This is known as reverse saturation current. So I will come back to this slide, but let's revise everything that we have seen here. Mostly we started from this particular question. In this particular question, why I picked this particular question, you understood. My major target was to make you realize about the current. So we realized one thing, that current is decreasing with the distance. Because why it is decreasing? Because your excess hole concentration is also decreasing with the distance. And since your excess hole concentration is decreasing with the distance, then your concentration gradient is going down. So that current is also going down. And at a good enough distance, like at 5 LP away, at 5 diffusion length away, the current because of the diffusion would be nearly 0. So all the current from where it would be coming? It would be coming from the drift component. And how did I find out this particular current? I said that what we are ignoring whatever that is happening inside the depletion region. So inside the depletion region, there is no recombination, there is no generation. So whatever that is happening at the edge of depletion, if I am having a current at the edge of depletion, the same current can be copied. Whatever the current I am having here, the same current can be copied in the depletion region. And whatever the electron current I am having, the same current can be copied in the depletion region. So in the depletion region, there would be two current components. If I add both of them, that would derive my total current. So from here I got the expression of total current, and since everything is in the series, every one of them has to drive the same current. If they are driving the same current, from there we are getting this particular expression. Now one more important thing was how much electric field has been set up here. From the applied electric field, how much component of electric field has been set up here, that I needed to find out. So for that I framed a particular question. There I gave, there is a big length, semiconductor is there. From the junction, a particular length away, a particular distance away, I need to find out the value of electric field. What does that mean? That means at that particular length, I have set up the length in a manner that at that particular length, my current because of the diffusion is actually going down to 0 only. So current because of the diffusion is 0, that means all the current is coming because of the external electric field. So how much component of that external electric field has been put at this point? So that we find out and we got our answer. Okay, well and good. Let's see some discussion about reverse saturation current. Very simple discussion. So what you can see, this is the formula. Can I modify this formula in this manner? Sir, AQ dP by LP. This can be written as Ni square by Nd, AQ dN by Ln, and this can be written as Ni square by Pn naught, number of holes in n side under equilibrium. So that would be Ni square by Nd, and this would be Ni square by Ne. Okay, so it can be written in this manner as well. From here, what you can understand? from this particular expression, what you can understand? First thing, if Ni increases, then what will happen? I naught will increase. Okay. If EZ increases, band gap increases, then what will happen? More band gap means lesser Ni, and lesser Ni means lesser reverse saturation current, right? You know the relation, Ni equals to A T to the power 3 e to the power minus Eg by Kt, right? So if Eg is more, this whole value is lesser, Ni is lesser. If Ni is lesser, that means I naught is lesser. What about the temperature? Temperature always does whatever Ni asks him to do. So Ni says if temperature increases, Ni increases, then current will also increase. Because temperature and Ni are best friends. They are inseparable brothers. What all things we can see? Doping. If there is more doping, if doping is more, then current is, reverse saturation current is less. All good? All fine? Very simple thing. So they can ask like, what is the dependency of reverse saturation current on all these parameters? So all these parameters you can check, right? Ni, Eg, temperature, Na and D. So simply write down the expression. From the expression you will be able to understand. Okay. Now there is a certain formula that how your reverse saturation current would be changing with respect to the temperature. That means I am asking you, what will be my reverse saturation current at temperature T2 such that the reverse saturation current at temperature T1 is already given. So that would be equivalent to divided by 10 degrees centigrade. Or it's not necessary to write down 10 degrees centigrade, just write down divided by 10. What does that mean? That means for every 10 degree centigrade rise in the temperature, for every 10 degree centigrade rise in the temperature, the reverse saturation current becomes double. This is the multiplication sign, okay? This sign is multiplication. This dot is nothing but a multiplication. For every 10 degree centigrade, like if T2 minus T1 is 10, then what you will get? 10 by 10, that would be 1. So I naught at T2 would be equals to 2 times of I naught at T1. So for every 10 degree centigrade rise in the temperature, the I naught current, the reverse saturation current gets doubled. Shall I write down this statement? So I can write down this statement as well. So you just need to remember it. Okay, it is like a fact. You know that if temperature increases, I naught increases. How much it increases? So for every 10 degrees Celsius, or you can say 10 Kelvin, it is fine, right? 27 degrees Celsius could be written as 300 Kelvin. How 37 degrees Celsius would be written as 310 Kelvin. So here there is a rise of 10 degrees Celsius. So here also there is a rise of 10 Kelvin only. So when you are talking about the rise, when you are talking about the change, so change in Kelvin or change in centigrade, both are the same thing, right? So for every 10 degree centigrade or 10 Kelvin rise or 10 Fahrenheit rise, for every 10 degree centigrade rise in temperature, I naught gets doubled. The reverse saturation current gets doubled. Okay. Remember it as a fact only. So what they are saying, at 300 Kelvin, the current is 10 to the power minus 10 ampere. Find out the reverse saturation current at 325 Kelvin. So what will be your current at 325 Kelvin? So that would be equals to the current here multiply with for every 10 degree centigrade rise. So now the rise is 25 degree centigrade. 25 divided by 10. Okay, if it was 10 here, so 10 divided by 10, it would be doubled. If it was 20 here, it would be 4 times. Now it is 25, so it would be 2 to the power 2.5 times. So what is 2 to the power 2.5? That is 5.65. So the current would become 5.65 into 10 to the power minus 10 ampere. In ESC, these kind of questions can be asked. Okay. In ESC or PSU examination, very straightforward, nothing to learn here. This particular thing was good to learn, that Na increases, I naught increases, Eg increases, Ni decreases, I naught decreases, temperature increases, I naught increases, Na and D increases, I naught decreases. Now here, how it is depending on the temperature. For every 10 degrees Celsius rise in the temperature, the I naught current will get doubled. So I naught 2 would be equals to I naught 1 twice of T2 minus T1 divided by 10. So here the temperature is changing by 25 degrees Celsius. That means for every 10 degree it would get double, then for next 10 degree it would get 4 times, and then for next 5 degree how much it will get? So 2 to the power 0.5. So from here simply you write down the formula. So 2 to the power 2.5 into 10 to the power minus 10, you will get the answer. Very simple thing, very straightforward, right? So what is the ideal current characteristics we are getting? If you see this particular graph, if you see this particular expression, I ideal is I naught e to the power Va by Vt minus 1. So can you draw the graph? Yes sir, the graph is exponential. The graph is exponential like this. This is the graph we will be getting, right? Now there are a lot of assumption involved. So this was the ideal case. Everything was ideal here. Everything we have discussed about the ideal case now. But there were assumption involved. What was the main assumption? This was the main assumption. The depletion region has no generation and recombination of charge carriers. Sir, I did not understand the meaning of this particular statement. I will explain it. Okay, don't worry about that. Right? It is related to somewhat equilibrium condition. N into P equals to Ni square under equilibrium. But when we are applying the forward bias, N into P equals to Ni square is not maintained. N into P equals to Ni square e to the power Va by Vt is maintained. That means the electron and hole concentration has increased. And every device will oppose if its equilibrium is disturbed. The device was at equilibrium. He was resting. Okay. I am resting. Number of electrons multiply with number of holes. I am having Ni square. Suddenly you came, you gave it a bias, you disturbed its equilibrium, and now what the device will say? The depletion region will say that previously I was having N into P equals to Ni square, you disturbed it, so I won't let you disturb it. What I would do? I would generate some electron and hole pairs, or I would recombine some electron and hole pairs. So what your depletion width would try to do? Depletion width needs to decrease the electron and hole concentration, no? Because of the forward bias, the electron and hole concentration has increased, right? Va will be positive, Vt will also be positive. So this value is increased. That means electron and hole concentration in the depletion region because of the forward bias has increased. And since those concentration has increased, what depletion width will say? Depletion width will say, depletion region will say, I will oppose it. That means I need to kill the electron and holes that has been generated. Like those excess electron and holes that I am getting, those excess from here holes will be coming, and from here electrons will be coming. So those excess electron and holes that I am getting, these electron and holes needs to be killed. And what is the meaning of killing? Recombination. That means these electron, and what I will do, I will recombine them. Are you able to understand this point? What is generation? What is recombination? Generation means birth. And what is the meaning of recombination? Recombination means killing. Electron hole pair got recombined. That means electron and hole got killed. So what will happen inside the depletion region? Inside the depletion region, recombination will take place. So in forward bias, recombination would be happening inside the depletion region. And that recombination, if recombination is happening, that means there will be some recombination current as well. So that recombination we were ignoring. Okay. What did you understand? Because we disturbed the equilibrium of depletion region, we increase the number of charge carriers inside the depletion region. Depletion region will try to oppose it, and for that, what it needs to do? It needs to recombine these electron hole pairs. And because of that, some recombination current would also come into action. So this current would be there. Along with that, some recombination current would also come into action that we ignored. So this is the case of forward bias. In reverse bias, I will explain you generation current would come into action. Okay. So generation current would come into action in reverse bias, and in forward bias, recombination current comes into action. Okay. This I will be explaining. For reverse bias, I will be explaining in next video. Okay. As of now, we will talk about recombination current. So in brief, I have already explained by the diagram as well. I will again explain it, but I hope it is already clear to you. And the electric field in the neutral region was negligible, right? What we said, whatever the electric field, most of the electric field that we are applying, that has been applied to your depletion region only. That's why VA is coming, no? What is VA? VA was the potential that we actually applied to our PN junction. And that VA, we are saying that most of the VA is actually fed in the depletion width only. But you know that most of the VA will be fed to the depletion width, but not the complete VA. Some VA would be fed here as well, and some VA would be fed here as well. So this was also the assumption. Low level injection we assumed. What is the meaning of low level injection? That means when we made this diagram, when we made which diagram? Let's go back. Let's go back. Let's go here. Yeah. So when we made this diagram, we said that the excess holes that we are getting, they are never crossing the majority charge carriers, right? Basically, your PN XN will always be lesser than ND. So this is your low level injection. Okay. This was the condition of low level injection. So I know that holes are being injected. Holes from the P side are being injected to the N side. Electrons from the N side are being injected to the P side. But the injection is low level injection. The majority carrier concentration is not getting disturbed. The majority carrier concentration is still N type only. Okay, here majority carrier concentration is still P type only. So low level injection also we assumed. But what if there is high level injection? Then what will happen? So that we need to check, right? So another assumption was there. So a lot of assumptions are there. And series resistance is negligible. That means 0.2 and 0.4 are same only. The series resistance here, this resistance, we said that it is negligible only. Most of the resistance, most of the resistive path, this depletion width only will be having, and since it is having most of the resistive path, that means most of the voltage drop will be dropped across the depletion width only. So basically, we on top level, what do you understand? That we ignored this guy, RS, right? Along with that, we ignored whatever generation and recombination that is happening inside the depletion width, that we ignored. And another thing we ignored, that was low level injection. What if high level injection is there? What if a lot of holes from the P side is coming towards the N side? So that three things we are actually ignoring. And because of these three things, we get to our non-ideal characteristics of a PN junction. Okay. So we need to study non-ideal characteristics, but before that we will discuss one particular topic. So from here, which concept came into action? From here, the concept of non-ideal characteristics come into action. Non-ideal forward bias characteristics. This is something that we need to study now. Okay. Right. But before that, let's see a very simple concept of cut-in voltage. What do you mean by cut-in voltage? Cut-in voltage of diode. So this is our forward bias current equation. Okay. I am assuming that I naught is 10 to the power minus 9 ampere, Vt is 25 millivolt. So first answer me all these questions. If I am applying a forward bias of 10 millivolt, what will be the current? So what will be the current? Sir, I naught e to the power 10 milli divided by 25 milli minus 1. So that would be the answer. So you calculate it in a quicker manner. Very fastly we will calculate and we will write down the answer. So it is coming out to be 0.5. So this is nanoampere only. So I am writing down 0.5 nanoampere. What about the next one? So 20 divided by 25 e to the power minus 1. So 1.22. So this is coming out to be 1.22 nanoampere. 40 divided by 25 e to the power minus 1. This is coming out to be 3.95 nanoampere. 80 divided by 25. Don't look at the screen, do it on your own. Okay. If you are only looking at the screen, doesn't make any sense. 23.53 nanoampere. 160 millivolt. So 601.84 nanoampere. Next 220 divided by 25 e to the power minus 1. So you can see that 6.63 microampere it has become. Okay, almost 10 times. And what about from 220 to 230? So it has also become 9.9 microampere. So this is also like nearly 1.5 times. So what do you see here? that for some lower voltage, 10 millivolt, 20 millivolt, 40 millivolt, there is not a significant change. This was 0.5. From 0.5 to 1.22, not significant change. From 1.2 to 3.95, not significant change. This is also not significant change. But at some certain voltages, after some certain voltages, what is happening? There is very, very large change, 10 times, almost 10 times. This is almost 1.5 times, right? So the voltage where the significant change has started, that voltage is known as cut-in voltage. Because this graph that I have drawn, this will always not be exponential. Why? What is the meaning of exponential? This is the meaning of exponential, no? But what we are actually getting? We are actually getting this particular expression, Vt minus 1. So we need to ignore this one. If I am saying that this curve is exponential, that means this 1 has to be ignored. So what does that mean? That means e to the power Va by Vt should be sufficiently larger than 1. E to the power Va by Vt should be sufficiently larger than 1. Then only I can ignore this one, no? So at the point where e to the power Va by Vt starts becoming sufficiently larger than 1, that point is cut-in voltage. Okay. So initially our graph will not follow exponential curve. At a point where it has started following the exponential curve, that is known as cut-in voltage. For different semiconductor, the cut-in voltage is different. Okay. As of now, it might feel like that, sir, it is depending on Va by Vt only. But other parameters are also there. When we study non-ideal characteristics, I will define some neta value here. So that neta value also will come into action. So for different devices, different cut-in voltage are there. For silicon PN junction diode, the cut-in voltage would be 0.6 to 0.7 volt. For germanium, it is 0.2 volt. Okay. So it is observed that if you are having higher Eg, okay, if you are having higher band gap, then your cut-in voltage would be higher cut-in voltage. Okay, like basically you can relate it to this one as well. Like if a band gap is more, that means my reverse saturation current would be lesser. That means I will be having less current in forward bias. In forward bias, I would want more current. So if Eg is more, I am getting less current, right? If I am having more band gap, then my reverse saturation current is less. If reverse saturation current is less, then your total current will also be less, no? If this guy is less, then my total current will also be less. That means to get sufficiently large current, I will have to apply more forward bias voltage. So your cut-in voltage is that value of Va where you are getting significant amount of current. So if I am having larger band gap, that means I need to apply more potential to get significant amount of current. So this has been written on the next slide. The cut-in voltage, also called the threshold voltage or knee voltage of a diode, is the minimum forward voltage that I need to apply, at which the diode will start conducting a noticeable amount of current. Noticeable. Okay, start conducting a noticeable amount of current. So now this graph is given, I versus V characteristic is given. You need to find out which particular device, this is your X device, okay, Y device, Z device, 3 devices are given, and IV characteristics is given in forward bias. So for which device you are having the maximum band gap? What do you think? Which device is having the maximum band gap? So for device Z, you need to apply 0.6 voltage. That means the cut-in voltage for device Z is 0.6 volt. The cut-in voltage for device Y is 0.4 volt. And the cut-in voltage for device X is 0.2 volt. Before 0.2 volt, the current is nearly 0. Here also you can see that before 0.8 volt, the current is nearly 0. Nanoampere. Here 0.6 microampere. This I could have written as 0.6 microampere. So here I started getting some current. But before that nanoampere, this current was very low. So here kind of you can say that, sir, cut-in voltage is nearly around 0.1 volt, right? Because 80 millivolt would be 0.08 millivolt. So nearly around 0, after 0.1 volt or after 0.15 volt, I am getting some good amount of current, right? So here they have shown this current is nearly 0. This current is nearly 0. This current is nearly 0. So if your cut-in voltage is more, that means EG will be more, right? That means your band gap of EG would be more than band gap of Y would be more than band gap of X. So band gap of Z would be more than band gap of Y would be more than band gap of X. Okay. And how will you think of it? That sir, cut-in voltage is more. Cut-in voltage is more. What is the meaning of cut-in voltage more? That means I need to apply more voltage to get the sufficient amount of current. You need to apply more voltage to get sufficient amount of current. That means actual current that is flowing is very less. If actual current that is flowing is less, that means my band gap would be larger. So for Z, the band gap would be larger than Y and then X. Okay. So this is the answer. Very simple thing, very straightforward. Now we need to study the non-ideal diode characteristics in forward bias. A very, I would not say very important, but a very interesting topic. Usually it is understood with respect to equations, but with zero equation we are going to understand it. Equations and all, that is very easy to write down. I will copy some equations from some textbook, I will simply write down and then I will say, okay, this expression is there, that expression is there, you can compare it. No use. We will build up our intuition, we will see what is happening inside the diode without writing down a single equation. Okay. So without writing down the equation, we are going to see the known ideal characteristics of a diode in forward bias. Now, if you feel like that, sir, I don't have much time left for GATE examination. Sir, I don't have much time left for GATE examination. I need to prepare other subjects as well. So from here onwards, you can drop this video. Okay. From known ideal characteristics. Because till this date, there has not been any question from this particular portion. But this particular portion will be very interesting, that I can tell you. So if you are someone who is in second year or in third year or even in fourth year and you are having decent enough time, then I would highly recommend to do this topic. But if you feel like that, sir, I don't have much time left, then it is not that important. Okay. Not that important for the examination, because till this date they did not ask questions from here. And what I feel is that if they want to frame some good questions, so first they would go here. Like this kind of question they would ask. First they would ask this kind of question. Okay. Or they can ask questions from here, like which kind of question? This kind of question that we framed. So first they would ask these kind of questions. Then they would move to some non-ideal characteristics. Because here you would see that, sir, great intuitions will be used. Without mathematics, we are going to understand everything. Although a short trailer I have already given, that n into p equals to ni square was already there. Now, what is happening? The electron concentration and hole concentration has increased. So what your depletion width will try to do? Depletion region will try to oppose the increase of electron and hole concentration. What does that mean? That means it needs to recombine the electron and hole concentration. That means it needs to kill the excess electron and hole concentration. And because of that, some current would come into action. And that current is recombination current. Now that recombination current would come with your ideal current. So even if you are having this much of knowledge, then also it is fine. Okay, this much of knowledge will also be fine, at least for the interviews. But if you are someone who is preparing for ISC interview or some good interviews, like for master's interview, if you are preparing EDC, then I would recommend to do this topic. If you are preparing for GATE examination and you are not left with much of the time, then you can drop it as of now. Okay, but if you are having good enough time, then you should be doing this particular topic. So let me take a break and I will come back and we will start studying about non-ideal characteristics of forward bias diode. Okay, and one more thing, like in the end of this video, we are going to discuss one question. This question we are going to discuss. So this is not based on the non-ideal characteristics. This is very simple question, very straightforward. So you can solve this particular problem. Okay, don't drop this whole video. At least try solving this particular problem. Very straightforward question. It is not based on this non-ideal characteristics. This non-ideal characteristics would be mainly theory, and then we have written down some conclusion. We will write down the conclusion of whatever that we have studied, and then we will solve this particular question. This particular question. Okay, so you can try solving this particular question, or you can start watching this video from here. Important formula. So summary of the formula we are writing down here. Complete summary we will write down. So in 2 pages there will be summary, and then we will solve this question. Our job would be done. So if you want to avoid this discussion, whatever the discussion that I'm going to do here, you can avoid that particular discussion if you want to avoid it. Okay, but I cannot guarantee question might come up from here, but it is rare. Okay, it is rare that question would be coming up. In near future, like in 2027, in 2028 or 2029, they will start framing question from this particular topic as well. Okay then, yeah. So let me take a break and then I will come back. Yeah, welcome back. So we have been studying about diode in forward bias, okay, PN junction in forward bias. So now we need to see the known ideal characteristics. The ideal characteristics we have already seen, right? So what will happen? Actually, what is happening inside the depletion region? So this was your device under equilibrium. So this was your carrier concentration under equilibrium. So here under equilibrium, number of holes multiplied with number of electrons, that was equals to Ni square. But just as you have given a forward bias of Va, then inside the depletion region, number of electrons multiplied with number of holes. This is I am saying inside the depletion region, okay, not under equilibrium. So inside the depletion region, when forward bias is applied, so condition is number of electrons multiplied with number of holes is equal to Ni square e to the power Va by Vt. What does that mean? Va would be positive, Vt already positive. That means inside the depletion region, the number of charge carriers has increased. Inside the depletion region, number of charge carriers has increased, and we can verify it with the graph as well. Do you remember the carrier concentration graph? Sir, a lot of holes from P side would diffuse towards the N side, and then inside the neutral N region, they will be recombining in this manner. So this was your carrier concentration plot for excess holes, and this was your carrier concentration plot for excess electron, and eventually they will reach at the equilibrium condition only. But this was the plot on linear scale, right? We are going to plot on log scale. So all this plot, this particular plot and this particular plot, we are going to make on linear scale. Okay, so I will make the graph in this manner. In which manner? In this manner. So don't think that, sir, they are decreasing linearly. They will decrease exponentially only. This is your exponential plot only, right? Why exponential? Because actually we are making this particular plot on log scale. Okay, so since we are making it on log scale, then I know that my excess carrier concentration will decrease exponentially only. So here also it will decrease exponentially only. And inside the depletion region, I know that this is how the concentration would go. The electron concentration would keep on decreasing in this manner. The electron concentration would keep on decreasing in this manner, and hole concentration would keep on decreasing in this manner. So previously, this was your Ni square. This point was Ni square only, because number of electrons multiplied with number of holes, that was equal to Ni square. So here number of electrons multiplied with number of holes, that has become Ni square e to the power Va by Vt, that has increased. So by the graph as well we can verify it. So this kind of carrier concentration plot on log scale we are getting for forward bias. So in the graph as well we can see that this point has been shifted upward. If this point has shifted upward, that means the carrier concentration has been increased in the depletion region. Now every particular device, no matter whatever the device you see, that device would want to maintain its equilibrium. So whatever the condition that I was having at the equilibrium, the same condition I want to maintain, depletion region would be saying this particular thing. Depletion region will say that whatever the condition, whatever the number of charge carriers I was having under equilibrium, the same number of charge carriers I will try to maintain. So if number of charge carriers has increased, let's just say previously there were 2 holes only, now there has been 4 holes. So which phenomena needs to take place? Generation or recombination? Recombination means killing, generation means birth. That means the excess carrier concentration that has been generated, they needs to be recombined with the electrons, right? Or you can understand the phenomena with respect to electrons as well. Like previously I was having 2 electrons, but now we are having 4 electrons. So whatever the excess electrons that has been generated, these excess electrons needs to be recombined. That means inside the depletion region, recombination process would start. Sir, how recombination process start? That is not a matter of concern. Okay, it happens because of the trap energy levels, and that trap energy level should be right in the middle of the Fermi levels. So that is not a matter of concern for you. Okay, just you need to understand that some recombination would take place. Why recombination is taking place? Recombination is taking place because excess carriers have been generated in the depletion region, and the depletion region would want to maintain its equilibrium. So whatever the excess carriers are generated, those excess carrier needs to be recombined. That's why some recombination will start taking place. And if recombination is taking place, that means recombination current would come into action, right? So whatever the ideal current you used to write down, sir, I naught e to the power Va by Vt minus 1, this current component would come. Along with that, some recombination current would also come. So I recombination would also come. So there are actually, in non-ideal diode, there are actually two currents. One current that is coming from the ideal diode equation, that is I naught e to the power Va by Vt minus 1, and other one is because of the recombination. And this we are considering in the case of forward bias. In reverse bias, generation current would come into action. Why generation would come into action? Because in the reverse bias, you would see that this concentration is going down. So if carrier concentration is going down, then what it will do? Like previously you are having two holes, now you are having only one hole. That means holes need to be generated. So in reverse bias, generation current would be coming into action. But as of now, who is coming into action? Recombination current is coming into action. So complete theory have been written. So every semiconductor device tends to maintain its equilibrium, and if any changes occur, it tries to restore equilibrium through recombination and generation process. Under equilibrium, a small number of electrons also are already present in the depletion region. When a forward bias is applied, the barrier potential reduces and the concentration of electron and holes inside the depletion region increases. How it increases? N into P equals to Ni square e to the power Va by Vt. The depletion region now tries to return to its equilibrium state by recombining these excess carriers. This recombination gives rise to additional recombination current in the depletion region. Hence, the total diode current under forward bias becomes the ideal current, ideal diffusion current plus this recombination current. Okay. Now, sir, what is the formula of this recombination current? Not a matter of concern for you. So, to compensate this particular recombination current, what was the formula of ideal diode current? So, that was I naught e to the power Va by Vt minus 1. Plus some recombination current is also coming into action, sir. So to compensate this recombination current, what they did, they changed the formula and they introduced another factor that is known as ideality factor. So they introduced a factor called neta. Okay, this is known as ideality factor. Basically what they did, and let me tell one more thing, that this value could be either 1 or 2. So what they did, they applied some forward bias. Okay, let's write down this formula again. This formula is I naught e to the power Va by Vt, but in place of Vt, neta Vt we will write down. So what they did, they applied some particular Va, okay, and they got the current. They went into lab, they took a diode, they applied some particular Va, they got some current, okay, and then they applied this formula. So whatever the answer they were getting from the formula and whatever the answer they were getting from practical, they wrote down that particular thing. Then again they applied Va. Then they again wrote down the formula. They again saw the practical values. So by whichever the amount, the formula value and practical value was differing, based on that they made this formula that if sometimes I am putting 1 here, then my answer is matching. If sometimes I am putting 2 here, then my answer is matching. So based on that, this modified formula came into action. So this is your current equation for non-ideal diode. Now when this particular equation would take neta equals to 1 and when this particular equation would take neta equals to 2, that is our matter of concern now. What is our matter of concern? That's when it will take neta equals to 1 and when it will take neta equals to 2. The equation we have understood, recombination would take place, that also we have understood. Because of the recombination, that modified equation came into action. I naught e to the power Va by neta Vt minus 1. By default in the examination, if nothing is mentioned, you will take neta equals to 1. If nothing is mentioned, that means if nothing is mentioned, they are talking about ideal diode. If they are talking about non-ideal diode, they will mention the value of neta. But at what kind of value, at what kind of Va value? This is your applied potential. So according to the applied potential, when you will take neta equals to 1, when you will take neta equals to 2, that is our matter of concern, and this is something that we need to discuss. Okay, when neta should be taken 1, when neta should be taken 2. So that we need to discuss according to the applied voltage. So complete discussion we are going to do. So first let's see what was our forward bias ideal diode characteristics. This was our ideal diode characteristics. This was having exponential rise. If I plot the same thing on log scale, so on both of the side, if I can take log, then what kind of graph I will get? Linear graph, right? Sir, this is not completely exponential, I know that, but it is nearly exponential only, no? If I ignore this one, At higher value of VA, I can ignore this one. So nearly linear graph I will be getting, near linear graph, right? Nearly linear graph I will be getting in this manner. So I will make this kind of graph. This is my ideal characteristics. Ideal characteristics I would be expecting if I am drawing the graph on log I versus VA. This is your I versus V. This is your log I versus VA. But practically, what kind of graph you will get? So practically, I will get this kind of graph. So as of now, the graph is made in front of your screen, but we will explain all the region one by one. So this is the first region where you can see that, sir, rise is not that fast. Rise is slow, right? Here the rise is very fast. Then again rise is very slow. And then again rise is very slow. So you can see there are total 4 different kind of region. 4 different kind of region. Region 1, region 2, region 3 and region 4. And important, I would say this graph is important actually. If they want to frame a new question, then this is what they would be framing. They would ask, what is your non-ideal diode characteristics in forward bias? They would make this graph as well, because people would remember this particular expression. They would remember this expression as well. From this expression as well, it feels like that this kind of graph should be coming. But if neta value is 2, if neta is 2, that means a slow rise is there, right? Are you able to understand this point? E to the power 1 by 2, e to the power 1, which is larger? E to the power 1 is larger, no? E to the power 1 by 2 is slower. Like basically, if I make the graph of e to the power x and another graph I make e to the power x by 2. So if e to the power x is going like this, then e to the power x by 2 will go slower, right? Starting from the same point, but it would go slower, no? It would go slower. Is that clear to you? E to the power x by 2. Like at x equals to 1, it will throw the value of e to the power 1. At x equals to 1, it will throw the value of e to the power 1 by 2. So e to the power 1 by 2 will go slower and e to the power x will rise faster. So you can see in this graph, at some particular point, sir, why it is coming, every reasoning I will give. But as of now, let's see the graph. If you just see the graph, sir, here the rise is slow. Then the rise is fast. Then again the rise is slow. Then rise is very slow. That means somewhere the value of neta would be 2, somewhere the value of neta would be 1, somewhere the value of neta would be 2, or somewhere it might be 1. So that thing we need to discuss. So this is our low forward bias. Then this is our mid forward bias. Then this is our high forward bias. Then this is our very high forward bias. Right? Low forward bias, mid forward bias, high forward bias, very high forward bias. So all these scenario we are going to discuss. Is the point clear? Is it clear what we are doing? So on top level, on brief level, what we saw, depletion region was getting some excess carrier. It will try to maintain its equilibrium. What it will do? It will start recombining. Recombination current would come into action. So ideal current characteristics will be different. It will not be ideal current characteristics. It will be a bit different characteristics. So we have done the modification in the formula. The formula now has become I naught e to the power VA by neta Vt minus 1, where neta can either take value 1 or it can take value 2. Neta is known as ideality factor. So based on the applied voltage, this kind of graph we will be getting. It is given in Niemann, and very soon I think this graph could be coming in your examination. Very soon. Okay. So let's talk about one by one. So let's talk about low forward bias. Okay. This is your low forward bias. So what will happen under low forward bias? Like this VA value is very low. Let's just say it is some 10 millivolt only. So if this VA value is very low, that means this built-in potential is not changing much. Let's just say built-in potential is 0.3 volt. Okay. And this is 10 volt. That means now this VA will be opposing this built-in potential, but it will not be able to oppose much of the built-in potential, right? But some built-in potential will be reduced. If some built-in potential is reduced, that means some holes from P side and some electrons from N side will try to diffuse to each other side, right? Some holes from P side will try to diffuse to N side and some electrons from N side will try to diffuse to P side because built-in potential has reduced. Previously, the barrier was making sure that no diffusion or no drift can take place, or you can say diffusion and drift were equal. But now diffusion is happening, but very little diffusion is happening. But now what will happen? Just as diffusion has started, depletion region will say my carrier concentration has increased now, e to the power VA by Vt. So what is the value of VA? 10 millivolt. E to the power 10 millivolt divided by 25. So now my carrier concentration has increased. Previously it was Ni square, now it has become e to the power 10 by 25, whatever it is. So it has increased now. So what I will do? I will start giving some recombination current. So whatever the excess carriers that we are having, whatever the excess carrier we are having in the depletion region, what depletion region will say, that I will start giving some recombination current. So the ideal current component, what is the ideal current component? I naught e to the power Va by Vt minus 1. So this current component would be very less. Why it is very less? Because you know that e to the power Va by Vt 10 millivolt divided by 25 millivolt minus 1. So this particular part is very less. This is nearly equals to I naught only. We have seen, right? Just before cut-in voltage, the current is not that much high. So that means this particular part is actually very less. But recombination current would be dominating here. Are you able to understand this point? There are two factors, ideal current and recombination current. We applied very small bias. Then what really happened? That some holes from P side and some electrons from N side has come into depletion region. Now depletion region will oppose it, that means it will generate some recombination current for sure. I should not say generate recombination current because you will be getting confused. So it will be recombining the electron and holes. So there will be some recombination current for sure. Now two components are there, recombination current and ideal current. Now I can see that ideal current component is very less. So here recombination current component has come into action. And because of that recombination current, like this neta equals to 2, if neta equals to 1, that means it is ideal current only. If neta is equals to 1, if neta equals to 1, then I non-ideal is actually equals to I ideal only. But under low forward bias, what do you see? The ideal current component is lesser, recombination current component is more. So ideal current component would have risen up exponentially, but recombination current doesn't rise exponentially, it rises linearly only. Okay, I cannot write down the expression, but actually as far as I remember, NIW, so it rises with 1/2 power of potential that has been applied. So you don't need to care about that. Basically you know that ideal current component rises very fast, ideal current component rises exponentially, but your recombination current component doesn't rise exponentially. Okay, as far as I remember, there was some formula for this one, QNIW divided by something it was. So proportional to that depletion width. The recombination current component is actually proportional to the depletion width, but you don't need to focus on formula. Like I don't want to teach this particular topic with respect to formula, because if I write down the formula, it doesn't make any sense, right? If I write down the formula, the theory would become very easy for you. Okay, you see this W is increasing, then this current would go down. Doesn't make any sense. We need to understand by the intuitions. So intuition says two current components are there. The exponential current component is not dominating, but the other component is dominating, which is not exponential. That means now current rise will not be exponential. The current rise will be slow. Is that understandable to you? Two current components are there. One is exponential, and other one is, let's assume it is linear only, or whatever it is. I don't care about that, but it is not exponential. So this particular component is more dominating. This is not dominating. That means rise will not be exponential now. If this is not dominating, that means rise will not be exponential. It will be slower rise. So you can see that between 0 to some mid voltage, the rise is slower. Is that understandable to you? So this is the theory that has been written here. In region 1, the diode is under low forward bias. The applied voltage is not sufficient enough to significantly reduce the potential barrier. At this stage, only a small number of charge carriers across the junction, and the recombination within the depletion region dominates the total current. In the total current, there are two components, ideal current and the recombination current. So recombination current is actually dominating the total current part. The injected carrier concentration are small, so most of the current rises from the recombination of electron and holes inside the depletion region rather than the diffusion in the neutral region, right? Because of the hole diffusion or because of the electron diffusion, the current is very lesser, but because of the recombination, the current is very large. Okay, that's why the rise in current is at a slower rate compared to the ideal diffusion controlled region. Okay, so the rise will be a bit slower than what we actually expected. We expected a exponential rise. Exponential rise means on log scale it should be linear, right? Exponential rise on log scale it should be linear, but we expected this kind of rise with this much of slope, but actually we are getting this kind of rise which with a lower slope. Okay, and here the ideality factor would be nearly around 2. Okay, nearly around 2. Why nearly around 2? Because I know that the rise is slower. If the rise is slower, what does that mean? I have only two options. Either I take neta equals to 1 or I take neta equals to 2. So if rise is slower, that means what I should take? Neta equals to 2 only. Because if I take neta equals to 1, that means it will be the ideal rise. That means it will be exponential rise. But actually it is not exponentially rising. It is rising slowly. That means neta would be equals to 2. So at low forward bias, the neta would be equals to 2. This kind of question can be coming in your examination. Low forward bias, neta is equals to 2, or in the interview as well, this kind of question could be asked. How would you explain? Sir, at low forward bias, depletion width is not reduced much. That means because of the electron hole diffusion, much current is not coming into action, but carrier concentration inside the depletion region got changed. That means recombination current has come into action. Now the most of the current is controlled by the recombination current only, and because of that, recombination current is dominating. So, but recombination current will not rise exponentially. The ideal current could have risen up exponentially, but that ideal current component is actually very less. So most of the current is controlled by the recombination current, and because of that, sir, we are not getting exponential rise, we get somewhat lesser rise. That means here our neta value would be equals to 2. Let's go to our mid forward bias region. Okay, so now decent amount of forward bias voltage we are applying. Some decent amount of forward bias voltage we are applying. We are applying as much of voltage such that we are getting exponential current. Okay, decent amount of voltage we applied. That means decent amount of holes from p side have come to the n side, and decent amount of electrons from the n side have come to the p side. Now what about the recombination current? Recombination current will also come into action, because n into p equals to ni square it needs to maintain, but actually this particular thing is happening. That means n into p has gone up, so recombination current would also rise up. Surely your recombination current would also rise up. There is no doubt about that. In this case, let's just say there was 1 microampere recombination current. So in this case, under mid voltage, the recombination current would rise up. But what really happened? The ideal current component that I was having, that has risen up much greater than the recombination current. Much greater than the recombination current. Recombination current also has risen up. Why is that so? Because carrier concentration has increased. If Va is more, that means carrier concentration has increased. If carrier concentration has increased inside the depletion region, that means recombination current would rise up. But the ideal current component that we were having, what that was? Sir, I naught e to the power Va by Vt. Now, sir, Va is sufficiently large. Let's just say Va is 200 millivolt, or you can say to 0.2 volt. So if Va is 0.2 volt, that means you can see that this current component is actually rising sufficiently exponentially. Are you able to understand this point? So the recombination current, whatever the rise is there, that will not even be reflected in the final output. Surely recombination current is rising, but that rise is also very little. But the rise in the ideal current component is very high. That means in this particular region, you will be getting exponential response. That means here your current would be, here your I total would be nothing but I naught e to the power Va by Vt minus 1 only. And whatever the recombination component you are getting, that would be nearly 0. Why it would be nearly 0? It is nearly 0 compared to this guy. Okay, basically your I recombination is much lesser than I ideal. Okay, so this can be nearly nullified. If it is nearly nullified, that means what kind of neta value we can see here? Neta is 1. So here the rise will be exponential, and that exponential rise will reflect as linear on log scale. So this theory has been written here. I hope it is understandable to you. What we are saying, in region 2, the diode is under moderate forward bias, where the applied voltage has sufficiently reduced the potential barrier. As a result, a large number of charge carriers, holes from the p side and electrons from the n side, are diffusing across the junction into the opposite regions. In this region, the diffusion current will start dominating over the recombination current, although some recombination will still be occurring inside the depletion region, but the increase in the forward bias leads to a rapid rise in the carrier injection and diffusion, causing that total current to increase exponentially with the voltage. That means here our diode will behave almost ideally, and it will show us a neta value of 1. So your ideality factor neta would be approaching 1 only, indicating that current is mainly due to the diffusion in the charge carriers, not because of the recombination. Okay, so this theory has been written. I hope that concept of theory is also clear. Now, what do you think in region 3, what would be happening? You are increasing the forward bias more. So, sir, if I am increasing the forward bias more, that means current should also be increasing. If you are increasing the forward bias more, current should also be increasing. So, what do you think? What is the reason behind this lesser slope? Actually, it should be rising in this manner. But why it is rising in this manner? What do you think? Who has come into action now? The series resistance, right? This is your PN junction, no? Series resistance RS, depletion resistance, and then series resistance. Sir, these series resistance are actually very low. Depletion resistance is very, very high. But as you are increasing the voltage, the current is also increasing, no? So if there is sufficiently large current that is flowing through this RS, then what this RS will do? RS will also drop something. And these RS would always make sure one thing, what it will make sure, that whatever the VF that we are getting here, that VF would always be lesser than V built in. That means RS is actually taking very high drop. So if RS is taking very high drop, what you expected? You expected the current to rise exponentially. But how you expected the current to rise exponentially? In this manner. But the voltage drop is actually not equal to VA. What we used to write down? Sir, VA is nearly equal to VF. VA is nearly equal to VF. This is what we used to write down. But we have applied VA so much high that now your VA is not equal to VF. That means in region 3, here if I write down the theory, here what I would do, that sir, I am applying VA very, very high. And I know this is the condition, that sir, there is some series resistance, depletion resistance very high, and then there is series resistance. Whatever the drop that I get across the depletion region, that is actually VF. And this drop only will decide the current. Right? So whatever the VA that you are applying, that is not equal to VF now. VF is actually much lesser than VA. So your actually current is being controlled by this VF, not by this VA. The formula that we write down, I naught e to the power VA by VT. Here ideally what should have been written? VF should have been written. That whatever the forward voltage that is being dropped across the depletion region. So that should have been written here, but here we write down VF. Sorry, here we write down in the formula we write down VA, but actually, ideally VF should have been written. Now, but now you can see that, sir, since I am increasing the VA voltage, since I am increasing my forward bias, a lot of current has been flowing here. And because of that, a lot of current, a lot of drop would be made across RS resistance. Okay. And because of that drop, this VF value, I expected it to rise exponentially. Like I expected it to rise very highly, but it is not rising very highly. And if it is not rising very highly, that means my current will also not rise exponentially, but the rise would be a bit lower. But do you really think that here I should write down that my neta value will be equal to 2? Here should I write down that my neta value is equal to 2? How the concept of neta came into action? Concept of neta came into action because of the recombination current. Not because of anything else, like not because of this sheet resistance. This is a complete different phenomena, no? Right? So here also neta is 1. But what really happened here? The current equation that I used to write down, I naught e to the power V by Vt, in place of V, we are actually writing now Vf. And that Vf is nothing but Va minus some drop, which is 2IRS divided by Vt minus 1. So this much current is flowing now. So what really happened here? Where we used to write down Va, this Va was nearly equal to Vf. But in this case, now your Vf has become actually Va minus 2IRS. And this is sufficient enough. This time it is sufficient enough. So you expected it to rise exponentially with respect to Va, but actually now it is not rising exponentially with respect to Va because this 2IRS is also playing some role. So here you will not say, sir, neta is equal to 2. No. This would be a very good question in the examination. They can make the graph and then they can ask you, here neta would be equal to 2, here neta would be equal to 1, here what will be the value of neta? Neta is 1 only here. Neta is still 1 because recombination is not being dominated. The current is still dominated by this particular part only. The current is still being dominated by the exponential part only. It's just that in the exponential part, I expected it to rise very fastly, but it is not happening. Okay. And basically whatever the slope, let's just say here I am getting a slope of 45 degree. So here the slope will be more than 45, it would be 50 degree, right? Are you able to understand this point? Like this rise, this particular rise will still be faster than this rise. Whatever the rise that I am getting here, that is still faster than this rise. This rise was low because it was mainly dominated by recombination current. Now this rise is low because of the sheet resistance. Sheet resistance or series resistance are also taking some drop. Because of that, this rise is low. So both of the phenomena are having some differences. I hope you are able to understand those differences. Okay, so this theory has been written here. So in region 3, the diode operates under high forward voltage, where the injected current becomes quite large. At this stage, the effect of series resistance of the semiconductor and the contacts become significant. Okay, as the current increases, a noticeable voltage drop develops across these resistance. So a smaller portion of the applied voltage actually appears across the junction. Because of this, current doesn't rise exponentially with the applied voltage, but increases more slowly, showing a linear behavior. In this region, the ideality factor still remains 1, but the deviation from ideal behavior is mainly due to the voltage drop across the series resistance, not because of the recombination current. Okay, recombination current is still there, but that recombination current is not comparable to this guy. Okay, there is still some recombination current. Let's just say you are learning something, you are learning EDC, I am learning EDC, but my knowledge is still nothing compared to the professor of IITs, right? So it's the same thing. So we are also rising. Forget about the phenomena. Needlessly, मैं फालतू का example देके relate करने का try कर रहा था. Very simple thing. I am needlessly making it complex with giving needless example. Okay, so let's not go there. Very simple thing it is, right? Very straightforward. More VA current should have risen up, but series resistance has come into action. They are also dropping sufficient amount of drop. Because of that, the actual forward bias across the depletion region, that is not that much high, right? Although with the applied voltage it will rise up only, but how much it will rise up? It will not rise up very drastically, right? That's why the current is not rising exponentially. But neta is still 1 because recombination current is not being dominated. Okay, so if you see the book of Niemann, in Niemann only till this particular point graph is given. Okay, this particular effect is known as ohmic effect. Okay, it is known as ohmic effect, but not important. The name are not important. This particular region is known as ohmic effect, but it is not important. In Niemann as well, this region was not discussed, region 4. But in brief, I will tell you here what happens. Here, high level injection will take place. So till this point, what we used to assume, low level injection. This was the diagram for low level injection. What we used to say, the concentration of excess carrier will never ever become larger than the majority carriers. So here, whatever the excess holes are coming, they will never cross the number of electrons. Let's just say number of electrons is 10 to the power 16, then the excess carrier can become 10 to the power 9 or 10 to the power 10 or 10 to the power 11, but they will never be compared to number of electrons. But in region 4, what will happen? At very high forward bias, what will happen? The depletion width will become nearly 0. It will become very low. It will become very narrower. That means a lot of holes from here would come towards this side. A lot of electrons from here would come towards this side. So now what these holes and electrons will do? Now these holes and electrons want to diffuse. If they diffuse, current would rise up, right? But the concentration has become so much that their mobility will go down. Like basically there are two current components, no? One is drift, one is diffusion. So the drift component would nearly go down. Like whatever the potential that you are applying, the depletion width has become very narrower. So there would be some drop in the depletion region. There would be some drop here as well now. There will be some drop here as well, right? Now the neutral region will also start taking sufficient amount of drop. And because of that drop, because of that voltage drop, there will be some electric field. And because of that electric field, you will have some drift current component, right? We have discussed this ideal current equation. There I told you that diffusion current component would keep on going down. As you walk along the length, as you move along the length, the diffusion current component would keep on going down. but the drift current component would keep on rising up. But now a lot of holes have come into action. So what they will do? They will decrease the mobility of all the charge carriers. Is that understandable to you? Okay. Along with that, since VA is very large now, so n into P equals to Ni square e to the power VA by Vt. Since it is very, very large, that means in the depletion region, large number of carriers would come into action. That means recombination current would also be very large. So in region 4, what is happening? Sir, a lot of electrons are diffusing from P side to N side, from N side to P side, and a lot of holes from P side to N side are diffusing. That means, sir, diffusion current component should go up and we should get larger current. Right? But what really happened? The mobility of charge carriers got decreased because of a lot of holes and electrons. Like a lot of holes are coming, a lot of electrons are coming. That means there is not enough space to move. If there is not enough space to move, that means they are not able to move freely. If they are not able to move freely, that means current would be lesser. So the ideal current component that we were getting, that has become lesser. But recombination would be very high now. Recombination is depending only on one thing. What is that? That if charge carriers are increasing, recombination would increase. So if you are going from region 1 to region 2, like this was my region 1, then region 2, then region 3, then region 4, recombination current is always increasing. Like if charge carriers are increasing, then recombination current would always increase. Like if someone asks you, here recombination current is more, or in region 2 recombination current is more, you will say in region 3, because VA was higher. So recombination current always increases, but the difference was, here recombination current has some importance, but in this region recombination current was having no importance. Here as well recombination current was having no importance. Are you able to understand this point? So if I am increasing my forward bias, if my VA increases, then surely my recombination current also increases. There is no doubt about that. No doubt about that. But the thing is, in this region there was some importance of recombination. Why there was some importance of recombination? Because the ideal current component was very less. But in this case, in region 2, the ideal current component was actually very high. So whatever the recombination current we were getting, that was nullified. That was nothing compared to the ideal component. Same goes here as well. Whatever the recombination current that you are getting, that is nothing compared to the ideal current component. But here what will happen? The ideal current component has reduced, and now recombination current would be very, very high. Why recombination current would be very, very high? Because NP has increased very, very drastically. If it has increased very, very drastically, that means the recombination current would be also increasing very, very drastically. But your ideal current component is not increasing very drastically. Why it is not increasing very drastically? Because of a lot of holes and a lot of electrons, and because of that mobility is decreasing, and because of that current is not increasing very drastically. So this theory has been written, although no one will talk about region 4, only they will be talking till this point. Okay, this is the last one till region 3, but for region 4 as well, you just need to know that high level injection is taking place. Okay, what is happening? High level injection is taking place. So here what has happened? The number of excess carrier has gone above the majority carriers. So if I talk about the N side, so in N side, the number of holes, the number of excess holes have become larger than the number of electrons. So in region 4, the diode is under very high forward bias, where the injected carrier concentration becomes comparable to or greater than the doping concentration in the neutral region, a condition known as high level injection. Although a large number of carriers are present in the region, but not all of them contribute effectively to the diffusion current, because their mobility has decreases at such a higher carrier concentration. At the same time, the recombination current increases as more carriers are available, and the junction continuously try to maintain the charge balance. Due to reduced mobility and enhanced recombination, the effective flow of charge grows less rapidly with the voltage, because recombination current is dominating now, and you know that recombination current doesn't increase exponentially, right? So due to that, the effective flow of charge grows less rapidly. So the current will also not rise up exponentially, but it will rise up slowly only. So here the neta value will be slightly above 2. Okay, I said that neta can take value only 1 or 2, but in the case of a high level injection, it will be slightly greater than 2, So nearly 2 only I am putting here. Here also nearly 2 only, but here neta value would be 1. Here neta value would be 1. Is that clear to you? So this was your non-ideal characteristics. We could have written down the equation of current, like this recombination current equation we could have written down, and then I could have acted that something different I have taught. But mathematics is something that should not be very difficult to explain. But theory is something that like this would make you feel good, I guess. But if I have just written down the mathematics, then I would say that you see this expression. This expression is saying that this will happen at lower voltage, this will happen at larger voltage. Doesn't make any sense. But I hope now everything connects to you. Like even if you are not able to connect to region 4, then it is fine, because high level injection will never ever take place in your examination. Even if we study basic semiconductor physics, everywhere I said that low level injection would be there. Even if examiner has not mentioned in the question, you would know that it is low level injection only. So in your whole question paper, high level injection will never take place. Here the equation of current would also be different actually. In region 4, the equation of current would be completely different, and it is not even given in the book of Newman. That means it will not be coming in your examination for sure. Is that clear to you? Okay, so don't worry about this particular region. Here just you know that current, again recombination current would be very very high, and since recombination current is very very high, what does that mean? That means if recombination current is very high, what does that mean? That means neta would be nearly 2 or somewhat greater than 2, because the current will not rise exponentially, because ideal current component is actually going down. And here in region 3, sheet resistance is coming into action. In region 2, ideal situation, recombination current component is nearly 0. In region 1, a very less charge carriers are coming here. That means the ideal current component is not rising exponentially. Ideal current component is actually very low. Recombination current is playing the main role here. And since they are playing the main role here, that means they don't rise exponentially. They rise in some different manner. That's why we did not see exponential rise here, or we saw the rise with lesser slope. Okay, so this was your complete characteristics. I hope you have understood, and I hope you have liked it in a good manner. Okay, so let's write down the summary of all the formula that we have understood. Okay, so this was the ideal diode current equation. From here only, from forward bias, if they want to frame some question, they would frame from here. I equals to I naught e to the power VA by VT. I naught is reverse saturation current. What is the formula? AQDP PN naught divided by LP plus AQDN NP naught divided by Ln. So dN by Ln, dP by LP, P PN naught, N NP naught. In that manner, you somehow try to remember it. This you will be able to remember. I naught e to the power VA by VT minus 1. Some guy might be forgetting the formula of reverse saturation current. So that is AQDP PN naught divided by LP, AQDN NP naught divided by Ln. Non-ideal diode current equation, I ideal plus I recombination. Because of that, neta came into action. It could be 1 or 2. Now, sir, what will be the formula of depletion width? So depletion width would be nothing but this particular formula is there. You would know that, sir, depletion width would be going down. So 2 epsilon by Q, nothing would be changed here. Sir, what is changing in the forward bias? Sir, previously I used to write down V built in here. But now I know that, sir, there is some forward bias which is reducing this depletion width. That means something I need to subtract from here. So whatever the forward bias that I am applying, that I would be subtracting. If nothing is mentioned, then what I would say? My VF is equals to VA only. If nothing is mentioned, that means whatever the forward bias that you are applying, the same forward bias has been dropped across the depletion width as well. What is this VF? The forward bias that has been dropped across the depletion width. What is this VA? The actual forward bias that you are applying. Okay. So if nothing is mentioned, what I will say? Sir, whatever that I am applying, the same is dropped across the depletion region. But we have understood that at very high VA, at very high forward bias, completely will not be dropped here. Some drop would be there across the depletion region as well. Right? Okay. Now these formulas, what is this? This is your total hole concentration in N side under forward bias at x equals to xn. That was coming out to be Pn naught e to the power Va by Vt. What is this? Excess hole concentration on N side at x equals to xn. So that was Pn naught, whatever this expression was there, minus Pn naught, because we are finding out excess. So e to the power Va by Vt minus 1. And what about this one? Sir, excess hole concentration on N side with the function of x. So what this was? Pn naught e to the power Va by Vt minus 1, and it will decay exponentially. So e to the power exponential decay, right? What about this one? Np naught e to the power Va by Vt, Np naught e to the power Va by Vt minus 1, Np naught e to the power Va by Vt minus 1, decay exponentially but towards the negative side. Okay, and electron concentration are decreasing, that's why Ln. Hole concentration are decreasing, that's why Lp. What about the maximum electric field? Sir, the same formula, Q Nd Xn divided by epsilon. Total charge Q Nd Xn divided by epsilon, or Q Na Xp divided by epsilon. It's just that Xn and Xp would change, right? Xn and Xp would be find out from here. Are you able to understand this point? Xn, what would be Xn? So it would be Wna upon Na plus Nd. But now this W has changed. This W is this one. In place of V built in, we are writing now V built in minus Vf. Right? So W has changed now. That's why the maximum electric field will also change. Is that clear to you? And that maximum electric field will be lesser. Surely it will be less, no? Because depletion width is going down. If depletion width is going down, that means Xn is going down. If Xn is going down, that means maximum electric field is going down. Right? Like previously, we were getting this kind of graph. Now we will be getting this kind of graph. And in the reverse bias, we will be getting this kind of graph. In reverse bias, depletion width will increase. This was the depletion width of your. This will come for reverse bias. This is equilibrium, and this is my forward bias. So here this is my maximum electric field. Here this is the maximum electric field, and here this is the maximum electric field. Right? Okay, fine. Let's solve this numerical. This is not related with the this particular explanation. This is a simple numerical that could be coming in your examination, because again it is given in Niemann. Okay, so from Niemann only we are taking this question. So just read it out and you will be able to solve it. I hope you will be able to solve it. So consider a PN junction. Total forward current is given. Total forward current is given. That is 25. Okay, current density is given, not current. Forward bias, applied forward bias is given. So whatever that has been given, just keep on mentioning that. The diffusivity and the carrier lifetime, Ni value, epsilon value, all these things are mentioned. Complete ionization you need to find out. You need to find out the value of Na and Nd. Okay, Na and Nd value you need to find out. Na I need to find out, Nd I need to find out. So sir, this current equation is given. From here something I can do. This I understood, right? Along with that, what is given? The current due to hole injection from P side to N side is 20% of the total forward current. That means this forward current, from where it is coming? Two components are there, no? Right? There are total two components. Here in this current, what is the expression of this current? If I write down the expression of this current, here only let's write down. That is, sir, J naught e to the power Va by Vt minus 1. That is equals to 25 ampere per centimeter square. Sir, what is J naught? J naught is nothing but I naught by A, right? Okay, fine. Here I used to write I naught, but current density is given, that's why I am putting J naught. Okay, here this is ampere and this is area. This is area. So don't get confused. Now, what is the expression of J naught? AQ dP PN naught divided by LP plus AQ dN NP naught divided by Ln. So if I write down the J expression, that is AQ dP PN naught by LP, and then it would be multiplied with e to the power Va by Vt, right? E to the power Va by Vt minus 1 plus AQ dN e to the power Va by Vt minus 1. So this current component was coming because this current component, how it came? This was there because of the I hope you remember this diagram. Whatever the current was here, that was this component, and whatever the current that was here, that was this component. This was your p side. In p side, from n side electrons were coming, and in the n side, from p side holes were coming, right? So current, because of the excess holes in p side, yes or no, right? And this is because of the excess electrons. Everything for electron we are putting up here, no? So this is because of the excess electrons in excess holes in n side, in p side. So this is 20% of the total. So what is the 20% of this? 5. So this is your 5 ampere, and this is your 20 ampere. Say yes or no? So what you can see, area I should not write down. Forget about the area, right? So Q dp Pn naught. So let's write down the value of Q. Q is 1.6 into 10 power minus 19. What is dp? dp is diffusivity of electron and holes. dp is 10. What is Pn naught? Pn naught is, what will be Pn naught? Pn naught will be, it is the concentration of holes in n side under equilibrium. So this will be Ni square by Nd, right? So Ni square by Nd. Nd I need to find out, into Lp. What is Lp? Diffusion length, that is not given. So you need to find it out. So Lp and Ln. I guess we found it out already in some of the previous problem. Same values was given, no? So I guess we have already find it out. I just need to check somewhere. Yeah, you can see 22.3 and somewhere 35.35. 22.3, 35.35. 22.3. 35. So 22.3, 35.35. So here I will put 22.3 micrometer. Okay, e to the power Va value is given 0.65 divided by Vt. Vt value again is not mentioned, should have been mentioned. Okay, Va value is 0.65, no? Yes. Vt value 0.0259 minus 1, and that I will put equals to 5, because it is 5 ampere per centimeter square. So everything I have put in centimeter only. So you just solve this equation and you will get the value of Nd. Let's try solving it. So 10 to the power minus 19, this would become 10 to the power 1, and this is 10 to the power minus 4 here, so it would become 10 to the power 5. So here extra 10 to the power 5 we are having. Okay, so 1.6 into 10 into 2.25 divided by 22.3 divided by 5 into 0.65 divided by 0.0259, 0.322. .55, nearly around 2.55. Yes. So this is the answer we are getting. 2.55 into 10 to the power 15. Okay. You can do it on your own. Similarly, here as well you can apply the equation. Simply you need to apply the equation and get the answer. And don't feel like that, sir, calculation is very vast. No. This kind of questions can be asked in the examination. This much vast calculation can be asked. Again Q. dn was 25 divided by ln, or here ni square you put, divided by ni square by na, and ln was 35.35 into 10 to the power minus 4, and again the same factor here, minus 1, that is equivalent to 20 ampere per centimeter square. From here na value would come out to be 10 to the power 15, nearly around 10 to the power 15. That's it. Okay, so this was just to like, this kind of questions can be asked, nothing else. So that's why I took this question here. It could be taken before the summary as well, it could be taken before this as well. Just I wanted to end this particular video with this particular question, that what kind of numerical question could be coming in your examination. So this kind of numerical question can come, and here also we saw some numerical problem. No, this kind of numerical problem very important, surely it is coming, very soon it is coming. Okay, electric field they would ask, so this kind of question can come. And another type of question we have seen, this kind of question. So three kind of patterns are there. At the depletion age they can ask you the concentrations or current. Okay, or what they can do, they can ask you the electric field, because they want to know that, do you know that drift component is also there, so because of that drift component how much electric field is being set up there, that thing they can ask. Or they can ask simply that carrier concentration. So basically this formula is very important, comes down to this particular thing, that this formula is very important. Most of the things are being solved because of this formula only, or this formula. So 1 and 4 very important. Okay, if you know 1 and 4, then most of the numerical problem you will be able to solve. If theoretical questions are coming, then more than enough theoretical discussion also we have done, right? I hope you will not say sir less theoretical discussion is there. A lot of theoretical discussion is there. Okay, so yeah, that's it. Next video it will be based on reversed bias PN junction. Okay, so let's move to the next video now.